Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 2b, such as polynomial regression, decision tree regression, and random forest regression. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. In this video of Part 2b, we will discuss about 5 important areas such as polynomial regression, support vector regression, SVR, decision tree regression, random forest regression, and evaluating regression models' performance. First, we will discuss about the polynomial regression, and how to do it in practical way.
Hello and welcome back to the course on machine learning. Today we're talking about the polynomial regression. So let's get straight into it. We already know a couple of types of regressions. We know the simple linear regression, which we can see over here. Then we've also discussed the multiple linear regression, which is written out over here. And finally, we've got the polynomial linear regression, which is written out here. So notice how it's very similar to the multiple linear regression, but at the same time, instead of the different variables like x2, x3, x4, and so on, xn, we have the same variable x1, but it is in different powers. So instead of x2, we have x1 squared. Instead of x3, we would have x1 cubed. And so instead of xn, we would have x1 to the power of n. So basically, we're using one variable, but we're using the different powers of that variable. So let's have a look at when you'd use a polynomial regression, when it would come in handy. Let's say we've got a set of observations which look like this. Then the line that fits this data is obviously a simple linear regression. As you can see, it fits it quite well. But let's for a change say that the data set looked something like this. So if we try to use a simple linear regression here, which is expressed like that, you'll see that it doesn't fit quite well. So in the middle, you've got data underneath, and then as you go further, the data will be above the line. So how can we correct that? Well, we can try to correct that by using a polynomial regression. Let's have a look. So instead of the linear regression, we're going to conduct a polynomial regression, and that in this case fits perfectly. And what is the formula? Well, that is the formula for this particular case. Y equals b0, so that's the constant, plus b1 x1, so that's a simple linear regression part, but then we're adding the b2 x1 squared, and the b2 x1 squared gives it that parabolic effect, or that the curve becomes parabolic, and therefore it will fit this data better. As you can see, polynomial regression is a bit different to a simple linear regression, and at the same time it has its own use cases. So it's all comes on a case-by-case basis. You have a problem, and then you might try a simple linear regression, a multiple linear regression if you have many variables, or you might try a polynomial linear regression and see what happens. And sometimes the polynomial regressions do work better. For example, they're used to describe how diseases spread, or pandemics and epidemics spread across territory or across population. Polynomial linear regressions can be handy there, and they also have other use cases. So it's a matter of what works best. So it's always good to have more tools in your arsenal. And we have one final question left. The question is, why is it called linear still, right? So we saw those different powers, squared, cubed to the power of n, and so on. Why is it still called linear? And I'll show you what I mean. If you look on the left here, it says polynomial linear regression. So why is it still called a linear regression if it's a polynomial regression? Well, the trick here is that when we're talking about linear and non-linear, we're not actually talking about the x variables, right? So even though they're non-linear here, the relationship between y and x is non-linear, when you're talking about the class of a regression, you're talking, so whether it's linear or non-linear, you're talking about the coefficients here. So that's the interesting part. So whether or not this function, which we have here, so y is a function of x, right? And so the question is, can this function be expressed as a linear combination of these coefficients, that because ultimately they are the unknowns, right? So your goal when you're building a regression is to find these coefficients, find out their actual values, so that then further down the track you can use those coefficients to then plug in x and predict y, whether it's a linear, well, a simple linear, multiple linear regression, or polynomial linear regression. That's your goal, to find these b coefficients. And that's why linear non-linear refers to the coefficients. So an example of a non-linear regression would be if the equation was y equals b0 plus b1 x1 divided by b2 plus x2 or something like that, or a b0 divided by b1 plus x1. So a situation where you really cannot replace the coefficients with other coefficients to turn the equation into a linear one in regards to the coefficients, not the x values. So there you go. That's why polynomial regression is still called a linear regression. That's your fun fact for the day, and maybe you can show off to your colleagues. And also, because of that, the polynomial linear regression is actually a special case of the multiple linear regression. So that's just something to also kind of note, that this is a version of the multiple linear regression rather than a standalone, absolutely new type of regression. So I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. Today we're taking a step forward because we're going to implement a slightly more advanced machine learning model, which is the polynomial regression. And to introduce polynomial regression, I think the best way is to make the transition between what we did before and what we're going to do for the rest of this part about regression. So what we did before was simple linear regression and multiple linear regression. And as the names indicate, these are linear regressors. And from now on, we are taking a step forward in the sense that we are going to build new regressors that are not linear anymore. So polynomial regression is not a linear regressor, then we will build the SVR regressor, which is not a linear regressor either. Then we will build decision tree regression model and then random forest regression model, which are not linear regressors either. So that's why from today we are making some new kind of regressors which are slightly more advanced regressor, especially for SVR or random forest. This polynomial regression model that we're about to build right now is not that much advanced compared to simple linear regression and multiple linear regression, because we will just add a polynomial term in the multiple linear regression equation, which you know well now. But what's coming next with SVR and random forest regression will be based on more complex theory. And speaking of theory, I think the theory behind SVR is actually fascinating. But today we will implement polynomial regression, so let's start doing it right now on Python. Okay, so as usual we'll go to File Explorer to set the right folder as working directory. So we'll go to our machine learning AZ folder, part 2 regression, polynomial regression, and that's the right folder. Make sure that you have the position salary CSV file in your folder, and if that's the case you can click on this little button here to set this folder as working directory. Okay, and now we are ready to start. So to be efficient, we are going to take our data preprocessing template that we made in part 1. So let's select everything here, copy and paste it in our polynomial regression model. So and now we just need to change very few things. So the first thing we need to change is the name of the data set. So it's not data here, of course, it's position underscore salaries. Alright, and now let's see if we need to change some indexes here for the matrix of independent variable x and the dependent variable vector y. So to do this, the best way is to actually import the libraries first to look at our data set. So press Command and Control plus Enter to execute. Well imported, perfect. And now we can have a look at our data set because we imported pandas that we use here to import this CSV file. Okay, so I'm going to execute this. Data set well imported. Let's have a look. So I'm going to go to Variable Explorer here, and here's the data set. Let's double click on it. And now let's see what the mission is. So we are a human resource team working for a big company, and we are about to hire a new employee in this company. So this new employee seems to be great, a good fit for the job, and we are about to make an offer to this potential new employee. And now it's time to negotiate on what is going to be the future salary of this new employee in the company. And so at the beginning of the negotiation, this new employee is telling that he's had 20 plus years of experience and eventually earned 160k annual salary in its previous company. So this employee is asking for at least more than 160k. However, there is someone in the HR team that is kind of a control freak and always fantasized about being a detective, so suddenly decides to call the previous employee to check that info, that info about the previous 160k annual salary of this future potential new employee. But unfortunately, all the info that this person manages to get are these info here, that is, this simple table of salaries for 10 different positions in the previous company. So this HR member of the team runs a simple analysis on Excel or Google Sheets and actually observes that there is a nonlinear relationship between these position levels and their associated salaries. However, this HR person could get another very relevant info. This other relevant info is that this new employee has been a region manager for 2 years now, and usually it takes on average 4 years to jump from being a region manager to a partner. So this employee was kind of halfway between level 6 and level 7, and therefore we can say he was level 6.5. So now this HR guy is getting all excited because he's telling to the team that he can build a bluffing detector using regression models and predict if this new employee is bluffing about its salary. So at the beginning the team finds it a little weird, but is kind of curious to see what's gonna happen. And therefore here is the mission. This new employee is telling that its annual salary was 160k. Let's predict if it's truth or bluff by building a bluffing detector using polynomial regression. Alright, and now let's see what indexes we need to change. So when we look at this table here, we want to predict the salaries based on the different levels that we have, and then predict the salary of a 6.5 level here. So basically we just need these two columns here. We don't need this column because it's strictly equivalent as this column, you know? Actually, it's like we already encoded the position column here, you know, by associating each level to a position. Well, the table is already encoded here, and therefore we only need these two columns to build our machine learning model. Remember, the machine is the polynomial regression, and this machine is going to learn the correlations between the levels and the salaries to predict if the employee is bluffing about its salary. So we will not include this column in the matrix of features X, and therefore we will only take this column level here. So basically, in short, our matrix of features X will be composed of only one independent variable, which will be the level column here, and our dependent variable vector Y here will be this salary column here, containing all the salaries for the 10 different positions. Okay, so then what does that mean in terms of indexes? Well, this data frame contains 3 columns: the position column, the level column, and the salary column. Indexes in Python start at 0, so that means that this column has index 0, this column has index 1, and this column has index 2. So okay, in X here we will specify that we want the index 1, and for our dependent variable vector Y here we will specify that we want the index 2. However, there is something we can improve here, because, you know, if I execute these two lines here to create the matrix of features and the dependent variable vector, as I just did, you can see that, well, Y is a vector here, as we can see with this 10, comma, and nothing afterwards. But we can see that X is seen as a vector as well, because we only specified the index 1 here. But, you know, when we build a machine learning model, and especially here this regression model, we want our matrix of features to be considered all the time as a matrix and not as a vector here. So just to specify that X is a matrix and not a vector here, we will just add here colon 2, and don't worry here, I'm not including the second index here, because, you know, the upper bound of a range here in Python is excluded. But you will see that by doing that, now X will be considered as a matrix, because as you can see now, I'm going to execute this line, and now you can see that, you know, before we had 10 comma nothing, and now we have 10 comma 1, which means that now X is well seen as a matrix of 10 lines and 1 column. So it's always better to do that, you know, make sure that X is a matrix and Y is a vector, and you'll never get any warning about that or even errors. Okay, so that's it. We selected the right indexes here, so we can actually have a look at X and Y now. Okay, so here is X, here is Y. So here we have the 10 position levels, and here we have the 10 salaries associated to this 10 position levels. And our goal is to predict if this employee is bluffing by building a machine learning model that is a polynomial model that will predict the salary of this 6.5 level here, which is the level that this HR member of the team identified for this new employee. Okay, so let's do this, and let's move on to the next sub-step of the first pre-processing step. And the next sub-step is to split the dataset into the training set and the test set. And actually, the good news is that we won't need to do that here. And for 2 reasons. It's because when we look at our dataset, we can see that we have 10 observations. And when we have this very small number of observations, well, it doesn't make much sense to split the dataset into a training set and a test set, because we simply don't have enough information to train a model on one set and test its performance on another set. It wouldn't make much sense, and it would be a little ridiculous. And the second reason is that, you know, we want to make a very accurate prediction, because, you know, it's something real we are talking about here. We're trying to predict the central element of the negotiation we are having, that is this salary of this new employee. So we need to not miss the target here, and therefore we need to make a very accurate prediction. Otherwise the negotiation could turn pretty bad. And in order to make the most accurate prediction, we actually need to have the maximum info as possible, you know, so that the model perfectly gets the correlations of this dataset. So that's why only for this time we can allow ourselves to take the whole dataset to train our machine learning model. So that's what we're going to do, and therefore we are going to put all this section into comments, putting some 3 quotes here, and also at the end. Here we go. So now all this section is in comments, and therefore no training set and no test set will be created. Okay, and finally the last sub-step of the preprocessing phase, feature scaling. So will we need to apply feature scaling for our dataset here? Well, the answer is no, because polynomial regression actually just consists of adding some polynomial terms into the multiple linear regression equation, and therefore we will use the same linear regression library that we used as the one we used when we built our simple linear regression and our multiple linear regression models in the previous sections. So we are all good. No need for feature scaling, no need for splitting the dataset into the training set and the test set. Indexes are correct. We know what we have to do. Everything is all good. We are ready to move on to the next step. And so I look forward to seeing you in the next tutorial, because we will start building our polynomial regression model. Until then, enjoy machine learning. Hello and welcome to this Python tutorial. So in the previous tutorial we did the preprocessing phase, we imported the dataset, created our matrix of features X that is just composed of the levels column, the 10 position levels in the previous company of the employee we're about to hire, and the dependent variable vector Y, which is here, and that contains the 10 salaries associated to the 10 different levels of the matrix of features X. So okay, and then we didn't need to make any split of the data set into the training set and the test set, because simply we don't have much information, and no need to apply feature scaling either, because we're going to use the same library as we used for linear regression, which is a library that does the feature scaling itself to make more accurate predictions, and therefore no need to apply feature scaling here first. Okay, and now in this tutorial we are going to make two things. We're going to build a linear regression model, exactly like the ones we did in the previous sections, and also, of course, we're going to build a polynomial regression model and fit it to the dataset. So why creating these two models here? Well, it's simply to compare them. We're simply going to make this linear regression model as a reference to then be able to compare the results of polynomial regression to the results of this linear regression reference space. So let's build these two models and then let's see what happens. So we're going to build the linear regression model pretty quickly, because that's exactly what we did in the previous sections. So as you remember, we need to import the linear regression class from the sklearn linear model library. So let's do this from sklearn.linear model, import linear regression. Okay, so that's our class, and now we're going to create an object of this class, which will be the linear regressor object. Only this time we're not going to call it regressor like we did in the previous section, because simply we're going to make here two regressors, so we need to distinguish them, and therefore we're going to call the first regressor linreg and the second one linreg2, because the second polynomial regressor will be based on a linear regressor on which we will add some polynomial terms. So this regressor here for polynomial regression will be called linreg2. But the first one here for simple linear regression is going to be called linreg. Okay, so that's our first linear regressor. And now you know what to do. We need to call the class, the linear regression class that we just imported. Here it is. Don't forget the parenthesis. No need to input any argument here. We're all good. And now, of course, we need to fit this simple linear regression object linreg to our dataset, composed of not x-train and y-train this time, but x and y, because we didn't make any splitting of the dataset into the training set and the test set. Okay, so to fit this linreg object to x and y, we need, as usual, to use the fit method. So we add here dot, and then we pick the fit method here, and then in this fit method we need to input x and y as it's shown here, and therefore x, our matrix of features, comma, and y, our dependent variable vector. Okay, and now our simple linear regression model is ready to be created with only these three simple lines. So let's do this. I'm going to select this. Alright, press Command and Control plus Enter to execute. And here it is, simple linear regression model, well created. Okay, and now let's build the polynomial regression model. Okay, so to create this model, we are going to import a new class which is simply a class that will give us the tools to include some polynomial terms into the linear regression equation. And this class is called actually polynomial features. Okay, so let's import this class and then let's see what happens. So this class is actually in the preprocessing library. So here we'll type from sklearn.preprocessing. Here it is, enter. Alright, so preprocessing is actually a library that we already used for feature scaling, but this time it will not be to import the standard scale class, but the polynomial features class. Okay, so speaking of that, let's import it. So import, and then polynomial features. And now, as usual, when we create a class, we create an object of this class. And this object, we're going to call it poly_reg. Okay, so what is this polyreg object going to be? This polyreg object is going to be a transformer tool that will transform our matrix of features X into a new matrix of features that we're going to call xpoly, which will be a new matrix of features containing not only this independent variable, x1, but also x1 squared and, if we want, x1 at the power of 3, x1 at the power of 4, up to x1 at the power of anything we want. So basically it will just transform x, composed of only one independent variable, into a new matrix xpoly composed of this independent variable and new independent variables, which will be this independent variable at the power of 2, of 3, of 4, of 5, etc. Okay, so that's what it will do, and so let's create it right now. So we're going to call this class polynomial features as usual. So paste it here, and now of course we add some parentheses as for any class. And now let's see what argument we can input here. So I'm going to press Command I to inspect the polynomial features class, and here I get all the info. So the only parameter that we are interested in is the first parameter, the degree here, because this parameter will specify the degree of the polynomial features in our future matrix of features xpoly. So to start, let's actually pick the default value, which is 2, so I'm going to input here degree equals 2. Okay, so that's the first step, create this polyreg object. And now what we need to do is to actually create this xpoly matrix that I've been talking to you about so much. So let's create it and let's find out what it looks like. So xpoly here, I'm calling it this way. And so of course now we're going to use our polyreg object that we just created. So polyreg here. And so, you know, as I told you, polyreg is a tool that will transform the matrix of features X into this matrix of features xpoly by adding the additional polynomial terms into the matrix X. And right now, since the degree equals 2, we're adding only one additional polynomial term. But since we're transforming X into xpoly, we're going to use here the fit transform method, because first of all, we need to fit our object to X and then transform X into xpoly. So that's the one we use, fit transform. And therefore in fit transform here we input, of course, X. So let's do it. I'm going to select these 3 lines here and press Command and Control plus Enter to execute. Here we go, perfectly created. Now let's go to Variable Explorer and let's have a look at xpoly. And I'm also going to open X to compare. Okay, so let's see what happens here. So first of all, we have the original column here, the original independent variable, that is the variable of the 10 position levels in the previous employee's company. And now in this new xpoly matrix here, we have 3 columns. So let's first notice that the position levels column here of X is actually the column in the middle, and that corresponds to x1, the independent variable. And then we notice that this second column here is the squared of this first column here. So that's actually the polynomial term. That is that, you know, we call this independent variable x1, well, this variable is x1 squared, because as you can see, each value here is the squared of this value here. Alright, so we get that, and now what is this first column here? Well, remember in the multiple linear regression homework when we were implementing backward elimination, we had to manually add a column of 1s, you know, to include the constant b0 in our multiple linear regression equation. Well, here it's exactly the same. This polyRectool object that we created automatically created this column of ones here to include the constant b0 in the multiple linear regression equation. And so it automatically did that in case we need to use some libraries that need to have this column of ones here included in our matrix of features. Alright, and now we only have one thing to do left, is to actually include this fit into a multiple linear regression model. And to do this, we are going to create a new linear regression object that we're going to call linreg2. That's why I call the first linear regression object linreg, that was used to build a simple linear regression. And now we must create a new linear regression object to not make any confusion with the first one. And the purpose of this second linear regression object will be to include this fit that we made here with our polyreg object and our x-poly matrix of polynomial features into our linear regression model. So here let's create linreg2 equals linear regression, parenthesis, and now we need to fit this linear regression object to x-poly and y. So again, we're going to use the fit method here, and inside we're going to input x-poly and y. Alright, and now our polynomial model is created. So at first it can appear a little confusing, but basically when we take a step back, what we did is actually very simple and logical, because with these three lines here, we actually transformed our original matrix of features x into our new matrix of features x-poly containing the original independent variable position levels and its associated polynomial terms. And then once this new matrix of polynomial features x-poly was created, we created a new linear regression object, linreg2, that we fitted to this new matrix x-poly and our original dependent variable vector y. So that's exactly as if, you know, we were building a linear regression model, and in the first place we had this x-poly matrix here containing two independent variables, the position levels and the squared position levels. Okay, so now let's see what we need to execute. Here we executed the first three lines of this code section here, and so now we need to select the last lines to complete the rest. So press Command and Control plus Enter to execute. All good. And now our polynomial regression model is created and ready to reveal truth or bluff. So that's what we will be doing in the next tutorial, and I look forward to seeing you there. Until then, enjoy machine learning! Hello and welcome to this Python tutorial. In the previous tutorial we built two regressors, the linear regressor and the polynomial regressor. So this section is about polynomial regression, but we wanted to build this linear regressor as well to compare the polynomial regression results to this reference-based model here, which is the linear regression model. So we built those two models, and now we're going to visualize the results of both these models, and let's start by visualizing the linear regression results. Okay, so we're going to do exactly the same as what we did in linear regression, simple linear regression. We're going to start by plotting all the observation points. We have 10 of them, so that means that we're going to have the 10 levels on the x-axis and the 10 associated salaries on the y-axis. So these observation points will be the true results, that is the real salaries for the 10 different positions. And then of course we will build the predictions of our model. So first the predictions of the linear regression model, and then the predictions of the polynomial regression model. And we will compare these true values, these true observations, to the predictions made by the model. So let's do this. Let's start by plotting the true observation points. As in linear regression, we're going to use plt.scatter. And in parentheses, remember we first need to input the x-coordinates, and the x-coordinates are of course the values in this matrix of features x, which actually has one independent variable, and that's why these are all the x-coordinates of our observation points, corresponding to the 10 levels of our observation points. So here we input x as the first argument, then comma, and then we need to input the y-coordinates of our observation points. And of course these are going to be the real salaries, which are in this dependent variable vector y. So these are all the real salaries, and that's what we need to input for the y-coordinate. So y here. Alright, then what do we need to input here? maybe a color, because we want to make the distinction between the real observation points and the predictions made by our model. So let's add here a color, and we will choose the red color. So let's input it, color equals red in quotes. Here we go. We did the job for the real observation points. And now let's plot the predictions. So the prediction, we're going to use plt.plot. And then remember, what do we need to input here? Well, first, that's the x coordinates of our prediction points, so x here. But then, what do we need to input now for the y coordinates? So yes, indeed, the second argument here is the vector containing the y coordinates of our prediction points. And then what is this? These are going to be the predicted salaries predicted by our linear regression model of the 10 levels of this employee's previous company. So levels 1 to 10. And therefore we're going to take our object here that we created, that is this linear regression object, and therefore that is lin_reg. And then as usual we're going to use the predict method. So we need to add here a dot and then predict. Alright, predict. And so, you know, it's a method, so we add some parentheses. And according to you, what do we need to input in these parentheses? Well, since we want to predict the salaries of the 10 position levels, and since these 10 position levels are contained in the X matrix, well, it's a matrix of only one column, so this X column, therefore we need to input here X. Okay, and then the last argument that we can add to make a better plot is the color. So let's add the color here, same, and as I just explained, I'm going to choose a blue color for the predictions. Alright, so now we plotted the real observation points and the predictions, that is the predicted salaries of the 10 position levels predicted by our linear regression model. Great, and now let's make an even more beautiful graph by adding a title. So here we add plt.title, and then which title would you like? Well, what about truth or bluff? This way, that definitely explains the situation. And let's also precise that, you know, we are plotting the linear regression result, because then we will make the same graph for the polynomial regression. Okay, and don't forget the quote here to close the title. Alright, so that's done for the title, great. And now let's add a label to the x-axis, so it's plt.xlabel. Alright, and here very simple, let's say position level. Okay, and now let's do the same for our y label, plt.ylabel, and then in parentheses salary. Great, perfect. And let's not forget to add this plt.show to specify that the graph is ready and display it. Okay, so now let's have a look. Now it's the exciting part. It's the part where we have a look at the results. So let's do this. I'm selecting all the code section here and pressing Command and Control plus Enter to execute. And here we go. Let's enlarge the graph. Okay, so first of all, let's clearly make the distinction between the observation points that are the red points here, as you can see in red, and the predictions, which are the points on this straight line here in blue. So by the way, this is a straight line because that's the predictions of the linear regression model, and since of course the linear regression model is a linear model, then that makes a straight line as the fitting line. For a linear regression model, we will always have a straight line in 2 dimensions. Okay, so in red, real observation points, and in blue, predictions. Okay, so what can we interpret here? Well, first, these are not great predictions, except for this one here, where the red point is really close to its projected blue point on this blue straight line, and same for these points. Well, for the other points, we are quite far from the truth. Especially this one. Look, this one is really far from its prediction, because to get the prediction of a real observation point, what you have to do is to project this red observation point here on the line, like this, and to get the predicted salary, you then need to project this projected point on the line onto the y-axis, which contains the salaries. So basically that means that for this observation points, the real salary is about $1 million per year. Well, that's actually a huge salary, but I think it's the CEO. Let's hope so. So let's say it's the CEO. If we want to look at the predicted salary of the CEO, well, we need to go back here on this red point, project it on this blue straight line here, which is actually our model, and then project it again on the y-axis containing the salaries. And then here we obtain that the predicted salary of the CEO is about $650,000 per year. So, if we were negotiating the salary with the CEO and using this model to predict if the CEO is bluffing, then the CEO would definitely be very unhappy. He would even be furious. Okay, so that's why we need to make a better model. Not to satisfy the CEO, but to, agree with the real observations, that is this red observations. Because as you can see, it's difficult to make a straight line that will be close to all these red points here. And that's why we need to level up and make a non-linear model that will therefore not be a straight line here, and that will make much better predictions, that is much better predicted salaries that will help us in our negotiation. And speaking of our negotiation, let's have a look at the 6.5 level here. So as we can see, the 6.5 level is around here. So to get the predicted salary of this 6.5 level, we need to project this 6.5 level on our blue straight line corresponding to our linear regression model, and then project it again on the y-axis containing the salaries, and we get around $300,000. Okay, $300,000. That means that if this employee hadn't said anything about its salary, we could have offered him $300,000 per year. And this employee would definitely have been very happy. But the HR team would definitely not have made a great job at optimizing the costs. Okay, so I hope now you're convinced that not only for the CEO, but also for our negotiation here, that we clearly need to make a better model to fit it better to our observation points, our position level in the salaries. Okay, so let's now make this better model. So let's close this, and let's now visualize the polynomial regression results. So as usual, we're going to be efficient and copy all this. So I'm going to copy that, and we're going to paste it here. And now let's see what we need to change. Okay, so first let's change the basics. We're going to replace here linear by polynomial, and then that's okay. That's okay as well. We want to keep the real observation points, but that is definitely not okay, because these are the predictions of the salaries of the position levels predicted by our linear regression model. So here we need the predictions of our polynomial regression model. Okay, so what do you think we need to do? It's actually quite simple, but not that simple. I guess now what you must imagine is that we simply need to replace this linreg here by linreg2, right? That is what would actually come to mind naturally at first. But okay, let's see. Let's simply replace this linreg object by our linreg2, which is the object we created for our polynomial regression model. But as you can notice, this linreg2 object is actually not an object of a certain polynomial regression class. It's still an object from this linear regression class. So we actually need to add something here to get the predictions of our polynomial regression model. And what would be this something? If we go back to this section here, well, you notice that we actually first transformed the X matrix of features containing only the position levels into this X poly matrix of features containing not only the position levels, but also the polynomial terms of our independent variable containing the position levels. So remember X poly, where we can actually look at it. So this was the column of ones corresponding to the constant B0 in the multiple linear regression equation. And these are our position levels, and these are our polynomial terms of our position levels. Okay, so basically we transformed our matrix of features X into this matrix of features X poly containing the position levels. And we actually need to include that information here, because right now what we're doing here is just to take a linear regressor object. So there is no polynomial features here. There is not any polynomial term. So instead of putting this matrix of features X here, without the polynomial term, we actually need to input this new matrix of features containing the polynomial features. And so what we have to do now is to input X poly here instead of X. But imagine we have a new X here. Well, since this X poly was already defined as the transformation of our matrix of features X, well, if we want to add some new observations here and plot some new polynomial regression results, we would rather take this polyreg fit transform here that transforms any matrix of features you want instead of xpoly here. So that's why if I put this here, well, if you want to plot new polynomial regression results on some new matrix of features x, then what you only need to do is to replace x here, here, and here. So be careful not to fall in this trap. Don't use this xpoly here, because xpoly was already defined for an existing matrix of features x, and we want to make this code here applicable to any new matrix of features x. And that generalizes as well the visualization plot of the polynomial regression results, and therefore we have some very useful code here. Okay, and now the moment we are all waiting for. Let's see how the polynomial regression model fits better to our observation points, and let's find out what some nonlinear regression graphic results look like. So I'm going to select this code section here, and without waiting, let's find out about the polynomial regression results. And here it is. Let's enlarge this. Alright, so that's the polynomial regression results, and the first thing I have to say here is that unlike what we're used to before, having a straight line fitting the observation points, now we don't have a straight line anymore, we have this curve here, which is due to the fact that the polynomial regression model is not a linear regression model. So a very important pillar of your intuition now is to make the distinction between linear models and nonlinear models. A linear model in 2 dimensions will give you a straight line, and the nonlinear model will give you anything but a straight line. So it can be a curve, it can be some very complex mathematic distributions, it can be anything you want but not a straight line. Okay, and now let's interpret the results. Let's start with the CEO, who was very furious last time with the linear regression model. So the CEO, as we said, has an annual salary of $1 million. Okay, great. And now what does the prediction of the polynomial regression say? Well, we need to project this red observation point corresponding to the CEO onto our blue curve here, which is the polynomial regression model itself, represented in 2D. And we need to project this point again to the y-axis containing the salaries. And we obtain a salary of $900,000, much better than last time. And now let's look at the salary of our 6.5 position level. Okay, so I took the 6.5 level here, which I'm projecting on our blue curve, and then projecting it again on our y-axis containing the salaries, and we obtained a little more than $200,000. Better than last time. Remember, we obtained $300,000 with the linear regression model, and remember, this employee said that he earned an 160K salary in its previous company, so far this employee seems very honest, which is good. Oh, and by the way, of course, you can definitely see that this blue curve is approaching much better these real red observation points here than the linear regression model. Okay, but now we want to do even better. And to do this, we are going to add a degree to our polynomial regression model. And to do this, it's really simple. What we only need to do is replace this degree equals 2 here by 3. That way we're adding a degree, and now you're gonna see if I execute this code section here that will build a new polynomial regression model, but this time with a 3 degree, you will see what we will obtain. So I'm going to press Command and Control plus Enter to execute, and new polynomial regression model created. Okay, so this time it has 3 degrees. So I'm going to select this and show you. Okay, as you can see, this is quite different from what we had before. Alright, so that's the polynomial regression model with a 3rd degree. So as you can see, it's not convex anymore. We have this first curve here and then a new curve here, which actually makes it not convex. And we can actually see that this blue curve is approaching even much better the red observation points than what we had before. Not only the linear regression model, of course, but the polynomial regression model with degree equals 2. And by the way, as you can see, the prediction of the CEO salary is now very close to the real observation, the real salary. And that's because our model is much better now. And same for our 6.5 level. If we project this 6.5 level now, we obtain actually a value that is close to what this employee gave as its previous salary. So that's actually really good for us and for the employee also, because maybe he'll get a bonus for honesty. And now, just for fun, let's look at the results we get if we add even one additional degree, that is a 4 degree to our polynomial regression model. So let's replace here degree equals 3 by 4, and now let's execute this. Done. And now let's have a look at the graph. I'm pretty sure that we will get now a perfect model predicting the 10 different position level salaries perfectly. So press Command and Control plus Enter to execute. And here we go, that's what I thought. Okay, let's enlarge this. Clearly now you can see that the blue curve is almost passing by all the red observation points here. And now we hit the bullseye for the CEO salary because, you know, the prediction is nearly the same as the real salary of $1 million. So we hit the bullseye for the CEO salary, and we can be pretty confident that we also hit the bullseye for our employee's previous salary that had level 6.5. And therefore, we're going to use this model, this polynomial regression model, because it seems to be really accurate to predict the salary associated to the 6.5 level using the predict method. But before we make that prediction in the next tutorial, we can notice that we can still improve this plot. Indeed, what's happening here is that our code is giving us the predictions of the model for each of the 10 levels from 1 to 10, but then it's plotting some straight lines in between the predictions. We can actually have the real continuous curve by, instead of having only the predictions from 1 to 10 incremented by 1, we can have the predictions from 1 to 10 incremented by a higher resolution, like a 0.1 step. So let's do this for those of you who want to have a more advanced plot, sacrificing some simplicity in the code. It's actually not that more complicated, you'll see. What we just need to do is to create a new X here that we'll call XGrid, and that will contain all the levels plus incremented steps between the levels with a resolution of 0.1. So to create this new X, it's really simple. We're going to use this arrange function from NP that gives a range from one bottom value to one top value. So here we need to specify the lower bound, which is min X, that is level 1, and the upper bound, which is max X, that is level 10, and now we choose the incrementation of 0.1. And this will give us a vector, but what we need is actually a matrix. So now we will use the reshape function from NumPy to reshape XGrid into a matrix where the number of lines is the number of elements of XGrid, that is len XGrid, and the number of columns, which is of course 1. And now as you can see, if we execute this, XGrid will be a matrix of one column and 90 lines containing all the levels from 1 to 10 incremented by 0.1. Okay, so now let's of course replace X here by XGrid so that our model predicts all the salaries of these imaginary 90 levels from 1 to 10. And so now it's ready. Let's re-execute this. And here we go. You get a more continuous curve, which is actually the real curve of the polynomial regression itself. Alright, and now time to make the final prediction, and we'll actually do that in the next tutorial. Until then, enjoy machine learning! Hello and welcome to this Python tutorial. So in the previous tutorial we visualized the polynomial regression results and we compared them to the linear regression results to eventually realize that the polynomial regression model fits much better to our data set and our problem than the linear regression model. And now we just have one final step to do, and that is in this step that we're going to be able to say truth or bluff by predicting the previous salary of this new employee that, as a reminder, told us that its previous salary was 160k, and so we'll compare this value to our prediction, and that's where we'll be able to conclude if this employee was bluffing. Okay, so let's first predict this result with the linear regression model. So it's actually really simple. What we have to do is use the predict method of our linreg object from our linear regression class, and we actually already use this predict method. It's right here in the visualization of the linear regression results. As you can see here, we are using the predict method to predict the salaries of each of the position level contained in the matrix X. So we're going to take this predict method again, and actually we're going to take this line, only this part of this line containing the predict method. We're going to copy this and we will paste it here to predict the previous salary of this new employee. So this member of the HR team identified that this employee was level 6.5. So here, very simply, instead of predicting the values of X, because by inputting X here, this line of code linreg.predictX will return the 10 predictions of the 10 position levels contained in X. But we can also use this predict method to predict only one salary, only one value, and very simply, instead of putting a matrix here, the matrix X, we can simply put what we actually want to predict, that is the level 6.5. Alright, and that will return the predicted salary corresponding to this level 6.5. So let's see, let's check it out. Let's see what our linear regression model predicts as the salary of a 6.5 level. So we're going to select this and press Command and Control plus Enter to execute, and we get $330,000. And that's actually what we expected, because if we go back to the linear regression results plot, we can see that indeed for the 6.5 level here, well, if we want to get the predicted salary of the 6.5 level, we need to go up to the blue straight line here because it corresponds to the predictions, and then we need to project it on the salary axis, and we get indeed, as you can see, around $330,000. Okay, but that's the linear regression results, so that's definitely not the best model for our problem in our data set. So we are definitely not going to take this prediction by the linear regression model as a relevant factor of the negotiation, because right now we're negotiating with this future new employee and negotiating its future salary that is obviously based on its previous salary. So this is definitely not relevant. But now what is going to be relevant is the prediction by the polynomial regression model. And so let's predict the salary of level 6.5 according to the polynomial regression model. Okay, so to get this prediction, we're going to do the same thing as for linear regression. That is, we're going to take this part of this code here that visualizes the polynomial regression results, and this part actually is the part that predicts whatever we want. So we're going to copy this and paste it here. And same here, we will not predict all the salaries of the position levels contained in X. We are just interested in the prediction of the 6.5 level salary. So here we'll replace X by 6.5. So let's recap before getting the verdict about truth or bluff. Okay, so this future employee said that its previous salary was 160K. The linear regression model predicted that its previous salary was 330K. And now what is our polynomial regression model going to say? Let's see. Press Command or Control plus Enter to execute. And the result is 158K. So $2,000 below the salary mentioned by this future employee. So actually the verdict is truth and honesty. Great, so that's great for this big company who I'm sure will be happy to get a new honest employee in the company. And so now the HR team is happy about this result, even if it found this idea a little weird at the beginning. So I guess this is the end of this section about polynomial regression on Python. Now we're going to do the same thing on R for those of you who are also interested in R. So we're going to do the same steps, and it's going to be actually quite the same technique, and we'll see if we get the same predictions. Hopefully we do. So thank you very much for watching these tutorials. I hope you now understand well polynomial regression. I just want to say that, you know, this is the beginning of this course. We're still shaping our intuition and expertise of machine learning. So I wanted to use this simple example, you know, to get some visual results and some visual graphics. But I know that some of you are expecting more real-world business-related problems. Well, don't worry, you'll get that. As soon as we get the basics of machine learning, we will apply it to real-world data sets with all the complexities that it involves. So don't worry, we'll get to that. And until then, enjoy machine learning. Hello and welcome to this Python tutorial. So it's not actually a real Python tutorial because basically we will just make a template. It will be a regression template. And so why are we making this template? It's because we're going to now fit other nonlinear regression models on this same data set containing the position levels and the salaries, and therefore the code to build these models and visualize the results will pretty much look like this code that we wrote for polynomial regression. So we're going to make a regression template that not only will help us build very efficiently some regression models for our truth or bluff problem with the position salaries, but also you will be able to take this template, take it with you, take it at home, at work, and you'll be able to use it to make some predictions of real values on your data set. However, if you have more than 2 dimensions in your data set, then you won't be able to visualize the results on a graph, but you will definitely be able to fit, you know, your nonlinear regression model to your data set and then make those predictions of some new observation thanks to the predict method. Okay, so what we're going to do now is we're going to take everything here up to the end. There we go. Copy. And we're going to paste it in our regression template. There. Okay, and now we're going to change a few things. So in the pre-processing phase, we will of course not change anything because, you know, this imports the dataset. We have the correct indexes here, so that's fine. We don't need to change anything here. We will need to split the dataset into a training set and a test set for the same reason as for polynomial regression, because we have a very small dataset with only 10 observations. However, if you're using this regression template for your dataset to solve your business problem, then you will probably have more than 10 observations, and then you will need to remove the quotes here to not leave it as a comment, and therefore create a training set, you know, to train your machine learning model, and then test the performance on a separate test set. But for our problem, we will leave that as comment because we won't need this. Okay, and feature scaling, well, we will leave that as comment because most of the libraries we're going to use to build our nonlinear regression model actually don't require us to apply feature scaling manually. So actually that's okay for the pre-processing phase, and we can move on to the next steps. For polynomial regression, we fitted this linear regression model to our dataset as well to, you know, use it as a reference base to compare the linear regression result to our nonlinear polynomial regression results. Well, since we have the linear regression results in mind now, and we know that it's a poor model with a poor performance for this specific problem, we will actually remove it to only focus on our future nonlinear regression models. Okay, so speaking of nonlinear regression model, that's actually our next step, because here we build this nonlinear regression model and we fit it to our data set. So here, since it's a template, we will actually remove polynomial here, and you know, we can replace it by fitting the regression model to the data set. Okay, and we will remove everything here because this code section creates the polynomial regression model, and in the future sections we will build nonlinear regression models. So let's remove that and let's move on to the next step. So the next step is the visualization of the regression results. So I'd like to have this step as the last step of our regression template for two reasons. The first reason is that, you know, it's the most fun and exciting step, and the second reason is that our data set is non-linearly distributed. So we now know that we have to predict the salary of this 6.5 level with a non-linear regression model. So that's why I'd rather, you know, keep this visualization step as the most exciting step for the end after the predictions themselves. Okay, so the template is almost ready now. We will get rid of this because we have the linear regression results in mind. Alright, and same for this prediction here. Let's keep in mind that the predicted salary of the 6.5 level was $330,000. So let's just keep that in mind. But what we're mostly interested in are the future predictions of this 6.5 level salary with our future nonlinear regression model other than polynomial regression. Okay, so let's remove this. Almost ready, we just need to change one tiny little thing. It's the fact that the future nonlinear regression models will not be based on linear regression itself. What I mean is that, you know, we built our polynomial regression model just by adding some polynomial features into the multiple linear regression equation. So, you know, we built this linear regression object and we fit it to our transformed matrix of features X that we transformed thanks to this polyreg object that, you know, is adding the polynomial features to our original matrix of features X. But for the future nonlinear regression models that we're going to build, we will not do that. We will not create a linear regression object, and we will not transform the original matrix of features into a new one. So we will actually get rid of this linreg object here and here as well, and also get rid of this polyreg object and also its fit transform method that we have right here. So I'm gonna get rid of that here. Same for these parentheses, that were just the parentheses of the fit transform method. Here we go, and same here. Okay. So we're getting very close to the final template, and now the only last thing that we need to do is to take the old good method that we used, you know, remember when we had this ypred variable. So here ypred is not going to be a vector of predictions, but it's going to be the predicted salary of the 6.5 level. And here, since we got rid of the linear regression model, we're gonna create our regression model here by creating a regressor object from the appropriate class, and therefore, exactly like before, we will use here our regressor object with the predict method to predict the salary of this 6.5 position level. And that's it. That's actually the only thing that we need to write to predict this 6.5 level salary with any new nonlinear regression model. And therefore, same here. We will use our regressor object, which will be our nonlinear regression model, and then we add a dot here because we will use the predict method of this regressor object to predict, actually this time, the salaries of all the position levels contained in our matrix of features X, and no need to do any transformation in the future. And that's actually ready. Well, we can replace that by visualizing the regression results. Let's call it this way. And here same, let's just replace polynomial regression by regression model. Okay, so the template is ready now, Let's give a quick recap. So in this first part here, we do the pre-processing phase. We don't need to split the datasets into the training set and test set because we only have 10 observations. We don't need to apply feature scaling because most of the regression libraries don't require us to do so. Here we will create our future nonlinear regression models. So, we will import a class from a certain library, then we will create a regressor object that we will call regressor, and then we will fit this regressor object to our dataset using the fit method. And then in the next step, we will predict this salary of this 6.5 position level. And then in the last step, the most exciting step, we will visualize the regression results. That is, we will visualize the curve that our nonlinear regression model builds and fits to our dataset. Okay, now for those of you who are also interested in this code that plots the regression results in higher resolution and giving a smoother curve, well, we can add this optional code section below by, copying this one and paste it here and just specify here for higher resolution and smoother curve. All right, so remember what we need to do is to create this new X grid here that will contain all the levels from 1 to 10 plus the imaginary levels 1.1, 1.2, 1.3 up to 9.7, 9.8, 9.9. That is all the levels from 1 to 10 incremented by 0.1. So remember, to create this new array of levels, we need to use the arrange function of numpy, and then in this function we need to specify the lower bound, which is min x, that is level 1, then max x, which is level 10, and then the step, which is 0.1. Alright, so these three parameters here, but remember this gives us a vector and we would like a matrix, because in this plt.plot here, x must be a matrix, so that's why afterwards we used the reshape function to restructure this vector x grid into a matrix of len x lines and one column. So here, remember, we take our x grid vector again, dot, and then that's where we use the reshape function. And in this reshape function, we need to specify one argument here. So these two parentheses is the argument itself, and in this parenthesis, we need to specify the number of lines, which is len x grid, and the number of columns, which is 1. Alright, so that transforms your original matrix of features X into this new matrix X grid containing the 90 levels from 1 to 10 incremented by 0.1. And here, of course, we need to replace X by X grid, and then here as well, so that the models now predicts the salaries of those 90 imaginary levels from 1 to 10 incremented by 0.1. And therefore the blue curve will have a lot more points to plot on the graph because it's now predicting 90 salaries of 90 levels. So that's why by doing this we'll get a much smoother curve. Alright, so we're actually done with the model here. We can remove this to even more generalized, and here we'll just specify that that's where we create our regressor. Great, so now our template is ready, and so we are ready to use it for the next nonlinear regression models that we're going to build in the next sections. So I look forward to creating these new machine learning models with you, and until then, enjoy machine learning! Hello and welcome to this R tutorial. So we already built two regression models. It was the simple linear regression and the multiple linear regression, and these two models were linear models. And now we are going to the next level because we will start to build nonlinear regression models. So that means that for data sets where there will not be a linear relationship between the independent variables and the dependent variable, these nonlinear regression models will be very useful. And speaking of problems with nonlinear relationships, this is the kind of problems that we will have to deal with in the future sections. So in the future sections, we will build nonlinear regression models to solve nonlinear problems. And today in this tutorial we will start with polynomial regression. So as usual, let's prepare the workspace by setting the right folder as working directory. So right now I'm going to my machine learning AZ folder, part 2 regression, then section polynomial regression, and here is the right folder. Make sure that you have the position salary CSV file, and you can click on this more button here and then set as working directory. And now let's start with the usual first step of making a machine learning model. So this first step is of course the data preprocessing step. So to be efficient, I'm going to go to my data preprocessing template that we made in part 1. I'm going to select everything in that template, copy, and paste it in my polynomial regression model. This way. Okay, and now we just need to change a few things. So the first thing we need to change is the name of the dataset. So it's not data here, data was the name of the dataset in the preprocessing part, but now in this regression part, the name of the dataset is position underscore salaries. So here we'll write position underscore salaries. And now let's select this line and execute to have a look at our dataset. Okay, and now let's see what will be our machine learning mission. So we are a human resource team working for a big company, and we are about to hire a new employee in this company. So this new employee seems to be great, a good fit for the job, and we are about to make an offer to this potential new employee. And now it's time to negotiate on what is going to be the future salary of this new employee in the company. And so at the beginning of the negotiation, this new employee is telling that he's had 20 plus years of experience and eventually earned 160k annual salary in its previous company. So this employee is asking for at least more than 160k. However, there is someone in the HR team that is kind of a control freak and always fantasized about being a detective, so suddenly decides to call the previous employer to check that info, that info about the previous 160k annual salary of this future potential new employee. But unfortunately, all the info that this person manages to get are these info here. This simple table of salaries for these 10 different positions in the previous company. So this HR member of the team runs a simple analysis on Excel or Google Sheets and actually observes that there is a nonlinear relationship between these position levels and their associated salaries. However, and moreover, this HR guy could get another very relevant info. This other relevant info is that this new employee that is about to be hired has been a region manager for 2 years now in the previous company, and that usually it takes on average 4 years to jump from being a region manager to a partner. So this new employee about to be hired was kind of halfway between level 6 and level 7, and therefore we can say he was level 6.5. So now this HR guy is getting all excited because he's telling to the team that he can build a bluffing detector using regression models to predict if this new employee is bluffing about its salary. So at the beginning the team finds it a little weird, but it's kind of curious to see what's gonna happen. So here is the mission. This new employee that is about to be hired is telling that its annual salary was 160k in the previous company. Let's use polynomial regression to build a bluffing detector to predict if it's truth or bluff. Alright, and now that we get the problem, let's see if we need all the data set to train our machine learning model, which by the way is going to be the polynomial regression model. Remember, the machine is the polynomial regression model itself, and learning is related to the fact that this polynomial regression machine learning model will learn the correlations between the levels here and the salaries to predict any new salary of new levels that are not in this table here. For example, we want to predict the salary of level 6.5. Well, thanks to what our machine learning polynomial regression model learned on this info here, it will be able to predict the salary of level 6.5. Okay, so we noticed that in this data set, this position column is strictly equivalent to this level column. It's like we already encoded this position column, by transforming this variable into numerical variables, and therefore we will not include this position column in the dataset where we will train our polynomial regression model, and we will only use these two columns, level and salary, so that the independent variable column will be this level column and the dependent variable will be the salary column. So let's go back to our polynomial regression model, and here let's select these two columns we are only interested in. So to do this, we will reset the dataset. So I'm taking my dataset here, and again I'm taking my dataset, then brackets, and in this brackets here we will input the indexes of the columns we want to keep to train our machine learning model. So let's see what these indexes are. Okay, so we have three columns. Indexes in R start at 1. So this column has index 1, this column has index 2, and this column has index 3. So since we want to keep these last two columns, then we want to keep the indexes 2 and 3. Okay, so let's input that. To input this, we can simply input to column 3. Let's check it out. Let's select this line and execute. And as you can see now, our data set, if we look at it, only has these two columns, level and salary. So as a reminder, level is the independent variable and salary is the dependent variable. So we will use the correlations between the levels and the salaries to train our nonlinear machine learning polynomial regression model to predict some new salaries, such as the salary associated to a 6.5 position level. Okay, so let's go back to the polynomial regression model. Our data set is well imported now, it's well prepared, we have everything we need, and now let's move on to the next step. So the next step is to split the data set into the training set and the test set, and actually this time, and only this time, we will not do that. And the reason is that we only have 10 observations here. So this is a very small data set, and by the way, I chose this data set because we're still shaping our intuition of machine learning, we're still learning the basics of machine learning, and therefore I choose this simple data set because we have two dimensions here, so we will be able to plot the form of the polynomial regression model itself, as well as the future nonlinear regression models. Okay, so let's go back to our model, and as I just said, we won't need to split the data set into the training set and the test set. So what I'm going to do now is I'm going to put all this section in comments. So let's do this. Press Command or Control plus Shift plus C, and that puts all your selected lines in comments. So no training set and no test set will be created. Okay, and the last step now is feature scaling, and the good news is that we won't need feature scaling either. And the reason is simple, it's that because a polynomial regression model is actually a multipolynomial regression model with polynomial terms. Instead of having different features, like features that represent something very different, we are taking a first feature, which is actually the position levels from 1 to 10, and as the other independent variables that will be in our multipolynomial regression model, we will take the squares and other exponents of these levels here. Okay, so actually that's done. That was actually very simple. No need for training set or test set, no need for feature scaling, just some little changes in the dataset here with the indexes, and we're all fine. We're ready to build our first nonlinear regression model, that is the polynomial regression model, and that's what we will be doing. Hello and welcome to this R tutorial. So in the previous tutorial we did the preprocessing phase, we imported the dataset and selected only the level column and the salary column. Then we didn't have to split the dataset into the training set and the test set because, as you can see, the dataset is a very small dataset with only 10 observations. And finally, we didn't have to apply feature scaling. So that made this first preprocessing step pretty easy, and now we are ready to move on to the next step, which is to fit our polynomial model to the dataset. However, I would like to show you how the polynomial regression model is a much more powerful model for our situation. And the best way to show you this is to actually compare it to a baseline model, like a reference base model, which will be our linear regression model. That's why in this tutorial we will build two models, the linear regression model and the polynomial regression model. And then we will compare the results, we will compare the graphic results and also the predictions. So you'll be convinced that the polynomial regression model is a much more appropriate model for this problem, and the main reason for that is that our problem is a non-linear problem. Okay, so let's start by building this linear model. It's going to be very quick because we actually already did this. So we start by creating our regressor that this time we're not going to call regressor because we will build two regressors, the linear one and the polynomial one. So we will call it linreg. Here we go. And then later we will call our polynomial regressor polyreg. So linreg equals, and then remember we have to use the LM formula, and so we need to add some parentheses here, and then let's remind ourselves what we need to input by pressing F1 here to have a look at the arguments. Okay, so remember the first argument is formula, so the formula is very simply the salary that is our dependent variable tilde, so I just pressed Alt N, and then a dot here to take all the independent variables, but actually there is only one independent variable, so the dot here is strictly equivalent as just writing level. Okay, so perfect for the first argument, and then what is the second argument? It's data. So data, okay, so let's add this argument, data equals, and now let's see. Okay, so in the linear regression section we actually used the training set here as the data argument to train our linear regression model, but as we explained before, here we did not split the dataset into the training set or the test set, so we are simply going to train our model on the whole dataset itself, because it's a small dataset anyway and we want to have the most accurate prediction. So here simply we will just input dataset. Alright, and our linear regression model is ready. We are actually ready to build it, so let's just do it. Let's build our linear regression model. I'm pressing Command and Control plus Enter to execute. Alright, linear regression made. We can have a quick look at the summary here. Summary linreg. So I'm typing this in the console and pressing Enter. And here are the statistical results of the model. We're doing this on R because, as you can see, it's really easy. On Python we would have needed to import a class, create an object, but here it's really easy, so we can have a look. And we can see that the level has 2 stars here for the level of significance, and is actually not a bad predictor of the salary. But wait for the polynomial model to see how it's going to be much better than linear regression. Okay, so now let's move on to the next level, that is the better model, polynomial regression, and let's build it. Okay, so as I mentioned, we're going to call this regressor poly_reg. Alright, this way. And since the polynomial regression model is actually a multiple linear regression model in which the independent variables are actually the polynomial features of one independent variables, as Carol explained in the intuition tutorial, well, we're going to use again the LM function as we did for linear regression. So here I'm just going to start by taking my LM function, add the parentheses, and we're going to input our 2 arguments, formula equals salary tilde, Alt N, and then this dot here. But don't worry, we'll actually represent something else. So far I'm just putting the dot, and you'll understand what's going to happen next, which will make our polynomial regression build correctly. So then comma, and then we add our second argument, which is still going to be the data equals dataset, because we're going to train our polynomial regression model on the whole dataset. Okay, so now you must be telling yourself, wait, but this is exactly the same as linear regression. Well, that's true, and that's why we need to add a little something here to make this model a polynomial regression model. And this little something that we're going to add is actually the polynomial features. The polynomial features are actually some additional independent variables that are going to be the level squared, the level cubed, level to the 4th, level to the 5th, up to any degree you want. These are these additional independent variables that are going to compose our new matrix of features in some way, which will actually be the matrix on which we will apply a multiple linear regression model, which will make the whole model a polynomial regression model. So in short, a polynomial regression model is a multiple linear regression model that is composed of one independent variable and additional independent variables that are the polynomial terms of this first independent variable. Okay, so now that we get this idea, you'll perfectly understand what we're about to do right now when building our polynomial regression model, because what we're going to do is to build this polynomial terms. And to that extent, what we're simply going to do is to add specifically a new column here in this data set, which will be the level squared. So we're going to call this new independent variable level 2, and let's add this new column right now. So to add a column in a data frame, we need to take our data frame, so it's data set, here it is, and then we need to add a $sign here, and then we can add any name here, which will create a new column of this name and add it into our data set. So we're going to call this column level 2, because we're taking the level squared of our 10 levels. Then we add equals, and then we actually need to give the formula of the values in this level 2 column of our data set, and this formula is therefore the levels in our data set at the power of 2. So very simply, we're going to take all the levels of our data set by taking our data set and same adding this dollar here to take the level column, which is here. I just have to press enter. So by doing this, I'm taking the level column that is all the values of the level column in our data set. And now I'm going to take the square of all these levels in our data set. And so to do this, very simply, I just add hat and 2. That's it. That will just create a new column which will contain the squares of our 10 levels in our data set. So let's see. Right now my data set contains only 2 columns, level and salary. And if I execute this, here we go. Now let's have a look at the data set. As you can see, I now have 3 columns, level, salary, and level 2. And as you can notice, the values in the level 2 column are the squares of the values in the level column. Okay, and now we can build our polynomial regression model, because now this dot here not only contains the level column, but also the level 2 column. So this will build a multi-polynomial regression model where the independent variables are the original independent variable and the polynomial term of this first independent variable. And if you want to build a polynomial regression model with a higher degree, well, you would need to do the same here. We can copy this line and paste it here and just add a level 3 column that will contain the cubes of the levels in the original independent variable level of our data set. And as you can see, it'll be very easy. I just need to execute this line, and this will add a level 3 column in our data set. And so now this little dot here will be the original independent variable level, the square values of our levels in level 2, and the cube values of our levels in the column level 3. You can add as many powers of levels as you want, but maybe we'll stop here. We will see what is the best polynomial regression for our model, and so we will see what we'll get with this one. And now let's actually build the polynomial regression model. If we select this and execute, press Command and Control plus Enter to execute, and done, our polynomial regression model is created. Awesome. So we're gonna have a look. Let's type summary in the console, polyreg, and let's press enter and let's see what we get. Okay, so now what we can see is that these level 2 and level 3 polynomial terms that we created are actually statistical significant variables. But actually this table here does not show the real deal of the polynomial regression model for our problem. You will be much more convinced in the next tutorial, where we'll be visualizing the graphic results, and you will perfectly understand why our polynomial regression, which is a nonlinear model, will make a much better job at predicting what we want compared to this linear regression model, because it's a linear model. So we'll check that in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in the previous tutorials we made our first 2 steps of building our polynomial regression model, which were to pre-process the data, and actually that was really simple because we just needed to import the dataset and select the columns of interest. And then we fitted 2 models to our dataset, the linear regression model and the polynomial regression model. So we built the linear regression model as a reference of comparison of the polynomial regression model that we also built. And speaking of comparison, in this tutorial we are going to visualize the graphic results of these 2 models, and therefore we're going to make 2 plots here, 1 plot for each model where we're going to see the real observations and the predictions, and it's in this tutorial that you're going to be convinced of how more powerful the polynomial regression model is compared to the linear regression one. So right now, let's write the code to visualize those results. So we're going to do this with ggplot2. In case you didn't follow the linear regression tutorials on R, I'm just going to write the line to install the ggplot2 package. I'm not going to install it, but it's just in case you don't have it. And to check that, you need to go to the packages here and check if you have the ggplot2 package here. And so if you don't find it in this list here, you need to install it. And to install it, it's really simple. You just need to type here install.packages. You can press enter here, and then in quotes you enter the name of the package, which is ggplot2. And then you just need to select this line and execute this line by pressing Command and Control plus enter, and this will install the ggplot2 package without any issue. I'm not going to do it because mine is already installed, but you can trust me, it will work perfectly. So I'm going to put that as comment by pressing Command Shift plus C. Alright, and now we can start to visualize the linear regression results. So as you can see in the packages here, the ggplot2 package is not selected here, so I'm going to need to select here. So either I can click here, or the better way is to automate the selection of this package thanks to the script. And to do this, we just need to add the line library and in parentheses the name of the package with no quotes, so just ggplot2 here, this way. And when this line will be executed, actually we can check it right now. As you can see, ggplot2 is not selected. I'm executing this line and now it's selected. Okay, so now that our ggplot2 library is selected, let's start building the plot. So we're going to do exactly like in simple linear regression. We're going to use the ggplot function, and then we're going to add the different components in the graph. So first we will add the real observation points thanks to the geomPoint function, and then we're going to add the predictions component thanks to the geomLine function. Then we're going to add a title to the plot thanks to ggtitle, and then a label to the x-axis with xlab, and a label to the y-axis with ylab. So very simple, exactly like before. We're going to make this graph step by step. Okay, so let's start with the first step. The first step is just to type here ggplot with parentheses, and that will initiate the plot. And now remember, we need to add a plus here, and that's where we start to add the different components. So the first component is the real observation points, and we are plotting them with the geomPoint function. So let's add here geomPoint, geom_point actually. Here it is, and now we input the arguments in the parentheses. Okay, so the first argument, remember, is the aesthetic function. So that's in this function that we will input the x coordinates of our observation points as well as the y coordinates. So let's do this. AES, or aesthetics function. So in this aesthetic function we need to input the x coordinates and the y coordinates of all our 10 observation points. So let's see what these coordinates are. Let's have a look at our dataset. So our 10 observation points are characterized by their levels and their salaries. The x coordinates corresponds to the independent variable that is the level column here, and our y coordinates will be our 10 salaries here associated to these 10 levels here. So in short, the x coordinates are the independent variable values, that is the 10 levels here, and the y coordinates are the dependent variable values, that is the 10 salaries here. Okay, so let's input that. So x here is level and y is salary. However, since we did not specify that the data is dataset here, our dataset, we need to specify where we're taking the levels and the salaries. And to specify that, we need to add here dataset $, so that R understands that we are taking the levels of our dataset here. So it's going to be the same for y. We're going to specify that we're taking the salaries of the column salary in our dataset. This way. Perfect. And now we can add another argument, because this aesthetic function was the first argument of this geomPoint function. And remember, we can add a second argument, which we will add because we want to add a color to our points to then make the distinction between the real observation points and the predictions. And so we're going to pick the red color. So here I'm going to add the color argument and set it equal to red in quotes. Alright, and now let's not forget to close the parenthesis of the geomPoint function, because this parenthesis was for the aesthetic function, and now we are all fine. Great, and now let's add the second component, which are the predictions. So I'm going to add a plus here and add my second component here. So the second component is, as I just said, the predictions, and we're going to add these predictions component with the geomLine function. So exactly like we did in simple linear regression. So geomLine here, geom underscore line, and then parenthesis, of course. And again, we're going to take the aesthetic function combined to a color. So I'm just going to copy all this, right, and paste it in my geomLine function. Alright, and now of course we will change a few things. So first, let's start with the simplest. Let's change the color. We're going to pick a blue color for our predictions. Here we go. And now what we need to change are the coordinates of our prediction points. So the x coordinates of our prediction points are still going to be the levels themselves, because we're just predicting the salaries of the 10 levels that we have in our dataset. So here we obviously need to take the only levels that we have in our dataset. So we keep here dataset $level. But then for the y coordinates, of course, something is going to change here, because by taking dataset $salary here, we're taking the real salaries of our 10 levels. That is the salaries that are in the salary column of our dataset here. So, of course, we need to remove this and replace it by something else. And what is this something else going to be? Well, of course, it's going to be the predictions of the salaries of the 10 levels according to the linear regression model. And to get these predictions, we're going to use, of course, the predict function. And so actually that's exactly the same as in simple linear regression. In this predict function, we first need to specify the regressor. So the regressor is called linreg, because you know we're plotting the linear regression result, and our linear regression model was called linreg. That's our regressor, so linreg here. And now the second argument, remember, is new data. So new data here, and that's actually the data points we want to make predictions on. So very simply, that's our data set, because we want to get the predictions of the salaries of the 10 levels of our data set. So here we input indeed data set. There, perfect. So we're good, because we already inputted the blue color for our predictions. Great. And now let's complete this graph very quickly by adding a title, so plus here, and then we use the ggTitle function to add a title. Can you see how it's simple? It's starting to get really intuitive now. We're plotting the real observation points with the geomPoint function, then the predictions with the geomLine function, and now a title with the ggTitle function. Well, everything will seem easier and easier for you. So for the title, we're going to add, as in Python, truth or bluff, just to give a funny name to our problem. And we're going to specify here that we are plotting the linear regression results, so we will just specify here linear regression. Alright, so that's it for the title, and now let's add an X label and a Y label. So for the X label, we're going to add simply here xlab, parenthesis, and quotes, and then level, because our x-axis will contain the levels, and then plus ylab, parenthesis, quotes, and salary. And done! The linear regression results are ready to be plotted. So let's not wait anymore, and let's immediately have a look. So I'm going to select all this. I don't need to select this because ggplot2 is already imported. And now let's press Command or Control plus Enter to execute. And here are the linear regression results. So let's zoom on it and let's interpret. Great! Okay, so what is the first thing to understand here? Well, the most important thing to understand is definitely that we need to make the distinction between the real observation points, that are the red points here. Each point corresponds to one specific level and the real salary associated to this level on the y-axis here. And then we have our predictions on this line. That is that for each level, let's take for example the level 5. When we project this level 5 here on this straight line here, this point is actually our prediction point, and we can get the predicted salary by projecting this point here on the y-axis this way. And so we get a little less than $250,000. Okay, so that's the first thing to understand. The red points are the real observation points, and the points on this blue straight line are the prediction points. Okay, Now, the second important thing to understand is that our prediction results is actually a straight line. And the fact that it's a straight line is due to a particular reason. It's that the linear regression model is obviously a linear model. Each time you build a linear model in 2 dimensions, you'll get a straight line. And I'm highlighting this because the next model we're going to visualize the results is going to be the polynomial regression model, and this model turns out to be a nonlinear regression model, and you will see that it will not be a straight line anymore. And now let's give some interpretation. So first of all, we can see that this linear regression model represented by this blue straight line here is not fitting our data set very well, because as you can see, for some observation points, the prediction is actually pretty far from the real observation. That's the case for this point, and same for this point as well, and this point, and especially this point. Let's have a look at this point, for example. Well, this point is the real observation point. It corresponds to a 10 level and a $1 million salary. So it's definitely the salary of the CEO, and so that's the real salary. And now if we want to get the predicted salary for this particular observation points that represents the CEO, what we need to do is project this point on this blue straight line here, that is our linear regression model, to get actually the prediction point. And now to get the predicted salary of the CEO, we need to project again this prediction point onto the y-axis that contains all the salaries. And so we obtain that the predicted salary of the CEO is actually $620,000 according to our linear regression model. So imagine we're negotiating with a future employee that is about to be hired, and that was the CEO in its previous company. Imagine how furious this person will be if we tell this person that we believe it's bluffing because we think its salary is around $600,000, whereas its previous salary was in reality $1 million. The negotiation would probably turn really bad. So that's the first example of how this model can give poor results that can have a very negative impact on the situation, like the negotiation we are having right now. So let's see if the negotiation would actually turn bad for our real situation, that is this future employee that is about to be hired and that has a 6.5 level and that is negotiating its salary by saying that its previous salary in the previous company was 160K. Well, let's see. The 6.5 level corresponds to this level nearly, and when we project this level to our regression model, that is this blue straight line here, and if we project again this point on the salary axis, we get a predicted salary of, well, it's more than $300,000 definitely, so actually we're way above what this employee said its previous salary was. So actually in this situation, in our real situation, the negotiation would turn well for us. But still, we want to get the accurate prediction, and clearly to do so we need to improve the model and make a nonlinear model which will fit much better the observation points here. That is, that we will make some kind of a curve that will approach much better all the red observation points here. So let's do this. Let's close the linear regression results and let's start to visualize the polynomial regression results. And you're going to see now how easy it is to go from the linear regression results to the polynomial regression results, because what we will simply do here is, select this and paste it here, and now you will see how we only need to change very few things. So as usual, let's start with the simplest. Let's replace linear here by polynomial. Okay, and now what do we need to change? Okay, so do we need to change something in the geom point function? No, of course, because we want to keep the same real observations, so that's okay. And then do we need to change something in the geom line function? Of course, yes, because here we are predicting the salaries of our 10 levels in our data set according to our linear regression model. So according to you, what do we need to change here? Very simply, well, actually we just need to change the regressor in the predict function, and instead of taking the linreg, which is the linear regressor, we're going to take the polynomial regressor that we called polyreg. And that's it. That's actually all we need to do to visualize the polynomial regression results. And you'll see that in the next sections, it will actually be the same. We will only need to change the regressor to plot the new graphic results of our future regressors. So that's very nice. We're actually ready right now to visualize the polynomial results. So let's do this without waiting. I'm going to select this and press Command and Control plus Enter to execute. And here it is. As you can see, this is not a straight line anymore. Let's zoom on the graph. Alright, so as I just mentioned, the first reflex to have as a machine learning scientist is that this is not a linear model anymore. And by the way, congratulations, you just made your very first nonlinear model. We're going to see plenty of other nonlinear models in this course, but this is your first one, so congratulations. So, as you can see, it's not a straight line, now it's a curve, and we can immediately see that the curve is approaching much better all the red observation points. And especially for the CEO here. The CEO wouldn't get mad now if we negotiated with him its future salary in a new company, because now the prediction is much closer to the real observation point. And let's check our employee that is about to be hired and that has a 6.5 level. Well, 6.5 is around here. And when we project 6.5 on our polynomial regression model represented by this blue curve here, we get a predicted salary. Here I'm projecting the point on the curve back again on the salary axis, and we get actually a salary that is coming much closer to the salary mentioned by this future employee, which is around 160k here. Well, we don't get the accurate prediction yet because that's what we're going to do in the next tutorial, but definitely this model is fitting much better the dataset. And now, just for fun, let's add a new degree to see how this model can still be much improved and almost passing by all the points very accurately as we add more degrees. So let's check it out. Let's close this and let's add a new degree. So very simply, what we're going to do is add a new degree here by copying this line, paste it here, and we're going to add a new column in our dataset, level 4, that will correspond to our original independent variable level at the power of 4. And so therefore here we need to compute it this way by taking the 4th power of level there. And now let's execute this line to add the level 4 column in our dataset. And you can check to see that it's here, level 4, perfect. And now let's reselect this to rebuild our new polynomial regression model with this 4th degree now. So executing, new polynomial regression model created, and now let's have a look at the results. So these are the previous results corresponding to a polynomial regression model with a 3rd degree, and now let's look at what happens with a 4th degree. So I'm going to select this and execute, and here are the polynomial regression results for a polynomial regression model with a 4th degree. Okay, so as you can see, we can zoom on it if you want. As you can see, the line is actually strictly passing by all the red observation points, and now the CEO would be even happier with the negotiation, or should I say even less furious, because the prediction now is actually almost the same as the real observation point. That is, the predicted salary is almost the same as the real salary. Okay, and same for our 6.5 level employee. When we project this 6.5 level here on the curve, and then project it again on the y-axis, that is the salary axis, we get a value around what he said, that is 160k. And for those of you who are interested in having a more continuous curve here like we did in Python, I will add the code for that job in the R file provided in this section. You can check it out for fun, and this is the model we're going to use to get the accurate prediction of the previous salary of this new employee that is about to be hired, and we will compare it to the salary that it pretended to have in its previous company, and eventually tell our final verdict whether it's truth or bluff. So I look forward to doing that with you in the next tutorial, and until then, enjoy machine learning! Hello and welcome to this R tutorial. So in the previous tutorials we did the exciting step. We created our 2 regressors, the linear regressor and the polynomial regressor, and we visualized their results. So if we look at our graphs here, well, if we take the first one that we plotted, that is the linear regression graph, we obtained this straight line here that, besides its name, indicates that it's a linear model, and we thought that this model doesn't fit to the data very well because, as you can see, most of the prediction points are far from the real observation points. And then we were more satisfied when we visualized the polynomial regression results. First with a 3rd degree, so that's the polynomial regression model with a 3 degree, and it's actually much better. We can see that the model is fitting much better to the data set, since obviously the predictions are getting much closer to the real values than the previous predictions with the linear regression model. So that was much better. And then we did even better by adding a new degree to our polynomial regression model, and we actually obtained this model that we have here. And now we can clearly see that this model is fitting very well the data set, because all the predictions are very close to the real values, and for some of them it's actually the same. So that's definitely an excellent model for us, because we are trying to make the most accurate prediction as possible. We are trying to predict the previous salary of a potential future employee that is about to be hired, and this predicted salary is at the heart of the negotiation, because this employee is telling that his previous salary was 160k and is asking for more than that, and therefore we are trying to predict if this 160k salary is the truth or a bluff. Okay, so now that we get this curve and now that we see that we have an excellent model for our problem, we are going to validate this model, and this is the model we're going to choose to make our final accurate prediction. And that is what we are going to do in this tutorial. So let's do it. I'm actually going to this new code section that I prepared for you. So a first one to predict the salary associated to a 6.5 level according to a linear regression model, and then the second code section will predict the salary of the 6.5 level according to our polynomial regression, this one right here with a 4th degree. Okay, so let's start with the linear regression prediction. So we're going to do exactly the same as in simple linear regression. We're going to use the predict function, but actually something that's going to be different and will interest many of you. This time we're not going to make some predictions on a whole test set, that is on a vector of observations. We are going to make a single prediction. That is, we're going to make a prediction of a single level, which is going to be the 6.5 level. So you're going to see that the syntax is going to change, the technique to make this prediction is going to change, but it's actually as easy. So let's do it. We're going to call this prediction ypred as before. So be careful, ypred was before a vector, and now it's only going to be a single prediction value. So let's still call it ypred anyway, and same as before, we're going to take the predict function. So let's here take predict, here we go. And now in this predict function, remember we need to specify first the regressor we want to make the predictions with. So that's the first argument, and then the second argument is the new data of which we want to make the predictions. Okay, so let's input the first argument. The first argument is our regressor, and since we're predicting the result with the linear regression regressor, and since we called this regressor linreg, then the first argument we need to input here is linreg. Alright, so that's our regressor, and now we need to input the new data of which we want to make the prediction. So this new data is, as you understood, a single element, a single observation point. And this observation point is actually the 6.5 level here. So what we'll do now is to actually, since this 6.5 level doesn't exist in our data set, we actually need to create a new data frame containing this 6.5 value. We're not going to add this 6.5 level in our data set. We're going to create a new data set of only one line and only one column, that is of only one cell actually, and this cell will contain the 6.5 level. So let's do this. The syntax in R to do that is very simple. We just need to type here data frame separated by a dot. So frame, here we go, data frame, and now as you can see it automatically added some parentheses, and in these parentheses we need to input level equals 6.5, and that's it. That's actually all you need to do to make a single prediction using the predict function with a specific regressor that is here, the linear regressor. Let's check it out. Let's select this line and execute. Okay, ypred correctly generated. So as you can see, ypred is in the values here. We can already see the predicted value of the 6.5 level salary, and it's actually $330,000. So much higher than what this employee mentioned its salary was. So that's actually a good start for us. But remember, we don't want to keep the linear regression model. We want to keep the most accurate regression model. That is, of course, the polynomial regression model. So what we're going to do now is make the same prediction but this time according to our polynomial regression model. So let's do this. Let's be efficient and copy this line because we will only need to change a few things, but you're going to see that this time it's not going to be that simple as here. It's going to be simple, but not that simple. We just need to add several arguments. And why is that? The reason is very logic. It's because since our polynomial regression model learned the correlations on this data set containing the level column and also the level 2, level 3 and level 4 columns, well, when we create this new data frame containing only the 6.5 level observation, well, since our polynomial regressor is based upon these 4 columns here, level 2, level 3 and level 4, then that means that in this new observation cell that we created for our level 6.5, we not only need to input the level, but also the level 2, the level 3 and the level 4. And that's what's going to change here. That's the only thing that is a little less simple than what we did before, but that's still very simple because as you can see, it will be very quick and easy to add these values. So let's do this. Let's not forget to change, of course, the regressor here. It's not linreg anymore, it's polyreg, because polyreg is the name we gave to our polynomial regression regressor in this formula right here. Okay? And so now, as I just explained, we just need to add here the polynomial features of our levels. So that means that we need to add level 2 right here. And don't worry, we don't need to compute it ourselves. We just need to add here 6.5 squared. And that will do it because, you know, level 2 contains the square values of the values in the level column. And that's why here we add level 2 equals 6.5 squared. And same for the other levels. We actually made a 4th degree polynomial regression model, so we need to add here 4 levels. And so I'm adding here level 3 equals 6.5 at the power of 3, and our last level, level 4, equals 6.5 at the power of 4. And that's it. It was only this little less simple thing to do, but now it's ready. So let's check it out, and actually we're about to find out the final verdict of the heart of the negotiation, which is the most accurate predicted salary that this future potential employee had in its previous company. So let's find out. I'm going to select all this and press Command or Control plus Enter to execute. Here we go. So what is the final value? It's $158,000, so very close to what the employee said. He said 160K and we predicted 158K. So that's awesome news because not only we can proceed to the right direction of our negotiation, but also we can now be relieved that this new future potential employee is very honest, and that's one of the best qualities to have in life, including professional life. So verdict, is it truth or bluff? Well, the final verdict is truth. So we're ending this tutorial as well as this section about polynomial regression on a good note. So happy ending. Not only the verdict is truth, but also you can be proud of having built your very first nonlinear regression model. So congratulations again. And you're gonna see that in the next sections we will be introduced to some new nonlinear regression models, and some of them are fascinating. So you'll see. I look forward to seeing you in the next section. I'll just add a final tutorial here, but that's not to build any more model. It's just that we're gonna make a regression template, you know, to build a lot more efficiently the next regression models. You'll have, of course, the code template, and you'll see how it will be very useful. So I look forward to seeing you in the next section. Congratulations again, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in this tutorial, we're not going to make any machine learning model, we're just going to make a template, and this will be our regression template. So it's a template that is going to be very useful for the next nonlinear regression models we're going to make, like the SVR model, the decision tree regression model, and the random forest regression model. So we're going to use this template to build the 3 next models on R, and also you can use this template to create a regression model for your specific problem, because as you can see, you will only have a few things to change so that you will build your machine learning model very efficiently. So let's make this template, and to make it we're going to go from what we did in polynomial regression and generalize the whole thing. So I'm going to take everything from here up to the end, copy, and I'm going to paste that in the template. And now let's make this template. Okay, so first of all, let's start with the beginning. So the beginning was about pre-processing the data. So actually there is nothing to change here. We will keep, of course, these two lines because we will work on the position salary CSV file and build our nonlinear regression models on it. And for the same reason as before, we won't need to split the dataset into a training set and a test set because this is a small dataset. And we will leave feature scaling as comments here, since most of the libraries don't require us to apply feature scaling manually. So all good for the pre-processing phase, and this will be the first part of our regression template. Great, now let's move on to the next part. So the next part is about creating the model. Creating the model and fitting it to the dataset. So first of all, in the previous tutorial we built two regression models, the linear regression model and the polynomial regression model, and that was just to compare the two results and to show you that the polynomial regression model was much more appropriate to our problem because it was a non-linear regression model as opposed to the linear regression model, which is a linear model. So we only did that so that you can understand very clearly the distinction between linear models and non-linear models. But now that it's getting pretty clear in our mind, we are going to get rid of this section here about linear regression, because now we get the idea. And we will only focus on the new non-linear regression models themselves without comparing them to the linear regression model. But keep the graphic results of the linear regression model in mind. Keep in mind that it was a straight line, not fitting very well the data set, and therefore was not much appropriate to our data set where the data is non-linearly distributed. Okay, so we're gonna get rid of this. Done. Now we only have this code section here that creates the non-linear regression model itself. So we're gonna get rid of this because this corresponds to the polynomial regression, and to generalize we will just add a comment here to specify that this is where we have to create our regressor right here. Okay, and here we can also replace polynomial regression by the regression model, and we are all good with this section. Okay, now let's move on to the next one. The next one is about visualizing the results. So for the same reason as what we did in this section to fit the regression model to the dataset, we will get rid of the graphic results of the linear regression model because we have them in mind and we only want to focus on our future non-linear regression models. So let's get rid of this, and now we only have the graphic results of our future non-linear regression model. Okay, and the great thing about this template is that in this section we won't need to change anything, well, almost anything, because we're going to replace polynomial regression by regression model, and we're going to change this polyreg regressor here by regressor, because before we called it polyreg because we also had our linear regressor linreg, and so we needed to make the distinction. But now, since we got rid of the linear regression model, we will call our future nonlinear regression model regressor here, and that's why we input regressor here in the predict function. So basically, when we get to this section, when we build our future nonlinear regression model, the only thing that we will need to change is actually the title here. Basically, we don't have anything to change here, and that's the great thing about this template. However, of course, if you're using this template on your dataset and your problem, well, the only thing that you will need to change are the names here of the independent variable and also the name of the dependent variable here. That is, you'll have to replace salary by the name of your dependent variable. But that's all. Okay, and we're finally getting to the last section of this code template, which is about predicting the final result to get our final verdict. Okay, so same reason as before, we're gonna get rid of the linear regression part for this. So here we go, goodbye. And now we're only left with the polynomial regression prediction. Okay, great. And so now we just need to change something here. Well, first it's the name of the regressor, because before the name of our polynomial regression regressor was called polyreg. And now, since we won't make the distinction between a linear regression model and our non-linear regression model, well, our regressor will be called regressor. So here, regressor. And here, for polynomial regression, we needed to input the polynomial features of our data frame that we created in our data frame. Well, we won't need to do this for the next nonlinear models because this is strictly specific to the polynomial regression model where, we need to add those polynomial features, and so we will get rid of this. and we'll get something very simple. It's actually this line that will perfectly predict the salary of this 6.5 position level. Because in our future nonlinear regression models, there won't be those polynomial features in the dataset, so we will only need the original independent variable here, and especially this 6.5 value of this independent variable. So that's why we have everything we need with this simple line. Okay, great. And now the last thing that I'm going to do is maybe to take this code section here, cut, and I'm actually going to place it between the creation of the model and the visualization, because I like to keep the best for the end. And for me, the best part, the most exciting part, is the part where we visualize our results. And for a second reason is that we know that our problem is a nonlinear problem, and that therefore we need a nonlinear regressor, and we're definitely already convinced of that. So that's why we don't need to execute this code section before this one to convince ourselves that we need indeed a nonlinear regression model. So therefore, for the next regression models, we will make the prediction before visualizing the results, and that's why I'm putting that here first. Okay, so I think the template is ready now. Well, maybe we need to change the polynomial here to generalize the template as much as possible. So we'll replace polynomial here by, well, actually let's just put predicting a new result. All right, and here we can replace polynomial regression by regression model. Alright, and now just to finish this template, for those of you who are also interested in getting a smoother curve in your regression model results, well, there is this trick we can do to increase the resolution, and we're going to do that right now. So it's just an optional code section that I'm adding here in this template. I'm going to copy this because we will have just a few things to change. And you know, for those of you who really want a very smooth curve when you visualize your regression model results, well, you can use the following code. So the trick is to actually create a new sequence of levels. That means that here, when we are predicting only 10 salaries of the 10 levels, well, what we're going to do now in this section is that instead of predicting only 10 salaries of 10 levels, we're going to predict a lot more than 10 levels. And to do that, we will build a vector of imaginary levels that will actually be levels from 1 to 10, incremented by 0.1. So that means that we'll consider level 1, level 1.1, 1.2, 1.3, up to 9.6, 9.7, 9.8, and 9.9. So that's what we will create in this sequence, and therefore here, instead of predicting only 10 salaries, we will predict actually 90 salaries of 90 levels. So that's the trick, and to build this sequence, it's actually very simple. We're going to call this sequence xgrid, you know, because xgrid will replace dataset $level here and dataset here, and this xgrid is going to be defined as sec, which is a function that builds a sequence. And so in this function we need to input 3 parameters, the lower bound of your sequence, so that's actually min dataset level, because by doing this we're taking the minimum of all the levels in your original dataset. Alright, then the next parameter is the upper bound of your levels, that is level 10, and therefore we do the same with the max here, max dataset $level. Alright, and the third parameter is the step, so that's where we increase the resolution and make our fitting curve smoother, because here we're going to take a step of 0.1, and therefore 90 levels will be created here from 1 to 10, incremented by 0.1. Alright, so that's actually done, and now we need to replace dataset $level here that originally took the 10 levels of our dataset, so we are replacing that by xgrid. And same here, we need to replace dataset here by a new data frame, because you know this new data argument here is expecting a data frame here, so we cannot replace it directly by xgrid here, because xgrid is not a data frame, it's a sequence, that is, it's a vector. So what we need to do here is use this little trick again. Don't worry, it's quite simple. We need to use this data frame, data.frame command here that will actually create a data frame, and in parentheses we're going to specify that we want to create a data frame of new levels. So I'm taking the variable level here, and then equals, and that's where you put xgrid, because you know, by doing this data frame level equals xgrid, we are just creating a new column of levels containing all the levels in this sequence xgrid here of levels. And that's it. This new code section is ready to plot your regression model results in a higher resolution. And actually we're going to specify here that it's for higher resolution and smoother curve. Alright, and that's actually ready. So you can try it on either, your polynomial regression model that we made in this section, or you can use it on the future nonlinear regression models that we're about to build, and you will see the difference between these two. But then if you want a more simple code, you can use this one, or if you have, for example, a dataset with 100 observations incremented by 1, then this is the code you need to execute, because then you wouldn't need a 0.1 step to build your different points of your fitting curve. Alright, so now the template is ready. We're actually ready to use it for the next nonlinear regression models that we're about to build. We will do that in the next sections, and you're gonna see how we will be so efficient at building them. So I look forward to creating these models with you. It's gonna be very fun, and we will make them in the most efficient way. Enjoy machine learning!
Secondly, we will discuss about the support vector regression, SVR, and how to do it in practical way.
Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hi everyone, and welcome to the Support Vector Regression, or SVR, Intuition lecture. SVR can be a bit of a challenge to clearly examine it without taking in a range of context, but we're going to take a look at it in a relatively simple term to condense the information. As you progress into the hands-on part after this lecture, and to the Support Vector Machine section later on in this course, it will help reinforce some of the information that we are going to discuss. So what is SVR? What can it support? Since you have seen linear regression, SVR has parallels, but also does things a bit different. SVR is a type of support vector machine that supports linear and nonlinear regression. So how can we look at that? If you imagine a street for our example, instead of trying to fit the largest possible street between two classes while limiting margin violations, SVR tries to fit as many instances as possible on the street while limiting margin violations. Also, the width of the street is controlled by a hyperparameter referred to as epsilon. And we're going to take a look at a visualization in a moment to help reinforce that. But just keep it in mind for now, and let's delve a bit further. SVR performs linear regression in a higher dimensional space. What does that mean? Try to think of it as if each data point in the training represents its own dimension. When you evaluate the kernel between a test point and a point in the training set, the resulting value gives you the coordinate of your test point in that dimension. The vector we get when we evaluate the test point for all points in the training set, the k vector, is the representation of the test point in the higher dimensional space. And once you have that vector, you then use it to perform a linear regression. And if we take a look at the following visualization, we can see what we referenced earlier. We are trying to fit as many instances as possible on the street while limiting margin violations. So you have, for our example, our street, and we are trying to limit those violations. We have our epsilon parameter that controls the width of the street, and also our support vectors, or the points within the street. And you could really see from this visualization what support vector regression is performing. Again, there are parallels and similarities between linear regression, since we are performing support vector regression, but the point is to limit the margins with epsilon and to find the support vectors within the street. And on a side note, SVR, and in particular Gaussian processes, are a very good method to use for efficient computations by pre-computing a training set and then using SVR to interpolate the results. Let's take a look at the requirements for SVR. SVR requires the following training set, which covers the domain of interest and is accompanied by solutions on that domain. The work of the SVM is to approximate the function we used to generate the training set, to reinforce some of the information we've already discussed. In a classification problem, the vectors x are used to define a hyperplane that separates the two different classes in your solution. These vectors are used to perform linear regression. The vectors closest to the test points are referred to as support vectors. We can evaluate our function anywhere, so any vectors could be closest to our test evaluation location. While we are working through this, and again, some of this information might be a little bit repetitive, but try to use the diagram that we looked at before, since it's an accurate representation of this information, and we're dealing with our example of the street. Use this as a reference. Again, it's containing our support vectors, our epsilon parameter, and its intention to limit that space. We aren't performing that direct linear regression, but we want to limit that space and have the support vectors within it. Let's continue. So how does SVR work? Or what steps are necessary to perform SVR? And we're going to get to the main part of the algorithm in a moment. But first, we need our training set as the first step. After that, we have to choose a kernel and regularization. We then have to form the correlation matrix. For the fourth step, you now have to train the machine to obtain the contraction coefficients. And then you can use those coefficients to create your estimator. So you now have covered a decent amount of information, but stick with me because we have a little more to go. For our next step is to choose a kernel. One of the prominent kernels for SVR is the Gaussian kernel. Kernel choice becomes important because if you choose a kernel that goes to 0 as the distance between the arguments grow, as you move away from the training data, the machine will return the mean value of the training data. In addition to choosing a kernel, regularization also is important, and it matters because due to the training sets with noise, the regularizer will help prevent wild fluctuations between data points by smoothing out the prior. And try to keep all these details in mind, so when you start working on it in the next lecture, in the hands-on part, It may help reinforce this information to sink in further. We are almost there, but we have to examine the main part of the algorithm now coming up. And then we'll do a recap to wrap it up in overview so we can digest some of these terms and information a little easier. We are now arriving to our correlation matrix. And mainly you are evaluating your kernel here for all pairs of points in the training set and adding the regularizer resulting in the matrix. Then we have the main part of the algorithm, the y vector of values corresponding to your training set, the correlation matrix, and then the unknown or set of unknown we need to solve for. In order to solve it, we have a pretty simple process, which is inverting the matrix here and applying it to the vector y, which you have right in this example. Once the a vector parameters are known, you can form the estimator. We then use the coefficients we found during the optimization step and the kernel we started off with to estimate the value for y for a test point to compute the correlation vector of k. Also, to find the inner product with the alpha vector. Finally, we compute the element of k as the following. Overall, we have to form the correlation matrix, then solve the matrix to form the estimator, and form the estimator for the support vector regression as the main steps of the algorithm. Alright, the intuition behind SVR can seem a bit challenging, but to recap, let's try to simplify it a bit further. SVR has a different regressional goal compared to linear regression. In linear regression, we are trying to minimize the error between the prediction and data. In SVR, our goal is to make sure that the errors do not exceed the threshold. What SVR does in this sense is that it classifies all of the linear predictions into two types: the predictor lines that pass through error bars drawn, and predictor lines that don't. The lines that don't pass through those bars are not acceptable because it means the difference or the distance between the predictions and the actual values at those points have exceeded the error threshold. And for one more time, we've seen the following visualization before, but it shows the clearest intention of SVR. What the algorithm is concerned with is controlling the threshold and support vectors within it. It's not exactly the normal form of linear regression as we can see, but to use the term threshold or epsilon, what's going on between the established points. As you move into the practical lesson, along with the SVM section later on in the course, it will become evidently more clear, as SVR in a sense is an extension of an SVM. But as always, if you have any questions, please feel free to share them. Enjoy the practical exercise with SVR and enjoy machine learning.
Hello and welcome to this Python tutorial. Today we're going to study our second nonlinear regression model, and it's going to be the SVR. So let's start right now. Let's start by setting the right folder as working directory. So we'll go to File Explorer here, go to our machine learning AZ folder, then part 2 regression, and now we are in support vector regression SVR. So that's the right folder. Make sure that you have the position summary CSV file, and if that's the case, click on this little button here to set this folder as working directory. Alright, and now let's take our regression template and let's copy everything from here to the top, copy, and let's paste it in our SVR file. Okay, and now you're gonna see how things are gonna be so easy. We basically just need to create our regressor here and to change if you want some text. So for example this here, let's replace regression by SVR. Alright, and we can also change that here, fitting SVR to the data set, and here we can also specify that we are plotting the SVR results. Okay, perfect. And now we only have to do the one thing important to do here, which is the creation of our SVR regressor. So let's do this. I'm going to remove this command line and immediately create our SVR. And it's going to be really simple. We will just import the SVR class from the scikit-learn SVM library, because you know SVR is actually a support vector machine SVM, but for regression. So the class SVR that we're importing is from the SVM library. So let's do it. Let's import this class from sklearn.svm import SVR. Alright, so that's the class we need to import, and now let's create an object of this class. So that's actually the SVR regressor itself that we are about to create. And as usual, we're going to call it regressor. Okay, and now since we want to make it an object of the SVR class, what we need to do is to actually call the class SVR and add some parentheses here. Let's have a look at the argument. Press Command I to inspect this class. Okay, and let's see what we have. We have many parameters. As for many machine learning models, we have the penalty parameter C that you can play with to regulate overfitting. But the most important parameter that we have here and that we need to focus on is the kernel. So the kernel is whether you want a linear SVR or a polynomial SVR or a Gaussian SVR. Well, these are the most common kernels. Then you have the sigmoid kernel. But the one we want right now is the RBF kernel. And why is that? It's because we know our problem is nonlinear, so we shouldn't use a linear kernel here, because an SVR with a linear kernel would make a linear machine learning model that would not therefore be appropriate for a nonlinear problem. And then we have the choice between poly and RBF. Both these kernels could work for our problem, but we're going to take the most common one, which is the Gaussian kernel, and therefore RBF here. So we're just going to input here kernel equals RBF, even if we don't have to. It's just to, keep track of what we're doing, because as you can see, the default kernel here is RBF, and that's why we don't really need to input that here, but it's just to know what we are doing. Okay, so actually that's all we need right now to create our SVR regressor. And now, as usual, we need to fit this regressor to our data set. That is, we need to fit it to our matrix of features X and our dependent variable Y. So to do this, we need to take our regressor object here we go, and then use the fit method. And as you can see here, we need to input X and Y. So X, our matrix of features, and then Y, our dependent variable vector. Okay, so as usual, as we did before, nothing changes here. And the simple 3 lines here create your SVR regressor. So actually the code is ready now. We don't have anything to do left. We are ready to visualize all the results and get our final prediction about this employee's previous salary. So let's do this without waiting. So we're simply going to execute the sections one by one. So we're importing the libraries here. Then we are importing the data set and selecting our matrix of features X and our dependent variable Y. So here we go, done. We are all good here. And now let's create our SVR regressor by selecting this code section here and execute. Alright, regressor created properly. As you can see, the default parameters are automatically selected. And by the way, we make sure we have the kernel RBF, which is important because we know our problem is nonlinear, and this kernel makes our SVR machine learning model nonlinear. So great. And now let's get the ultimate prediction. So remember, this employee that is about to be hired said that its previous salary was 160K. And now let's see what SVR says. Press Command and Control plus Enter to execute. Okay, we still have the suspense. To find out about this value, we have 2 choices. We can either type ypred here in the console or go to Variable Explorer. And here we see that ypred is $130,000. Well, that's not good at all. What's happening here? If we believed this value, the negotiation would turn really bad, because we would think that the employee is bluffing. But let's not draw hasty conclusions, and let's have a look at the SVR results here. So I'm going to select this section to plot the SVR, and let's have a look. And here is our beautiful SVR model here, this blue straight horizontal line. Great! Now I'm joking, this is not the SVR model, don't worry. So what do you think happened here? Why do you think we obtained this blue horizontal straight line here? Okay, let's go back to our code. So right now you must be thinking that I gave you a bad template, because I promised you that we only needed to create our data set here and then execute everything, and everything should work properly. But there is some other thing that I told you 2 or 3 times that is very important. I'll give you a hint, it's in the pre-processing phase. It's about feature scaling. Okay, let me explain. So, I told you that for most machine learning models, we don't need to apply feature scaling here because the libraries or the classes include feature scaling in their algorithm. Their algorithm written in the class And that's why we put this section in comment, because for example for linear regression, we actually didn't have to do this because it was included in the associated class. But here, we're using a less common class, which is the SVR class, and this class doesn't seem to apply feature scaling in its algorithm. And you know, this is probably due to the fact that the SVR model is a less common model, so maybe that's the reason why the class didn't include feature scaling. Well, let's actually check it out. Let's remove these comments here to actually apply feature scaling ourselves by executing this section here. But we are going to start from scratch and we're going to reset our whole code to, you know, make sure that we don't overdo anything. Okay, so restart kernel. Yes. Now restarting, connecting to a new kernel. Okay, so be careful, you know, we removed this section in comment, but as you can see, we're not creating any training set and test set here. So we need to actually replace x train by x, and then no need to do any transformation on a test set because there is no test set here. So I'm going to remove this line as well. And you know, to make it structured, I'm going to remove that line here and put it here. Okay, and let's not forget to remove y train here and replace it by y simply. And now it's all good. We're ready to feature scale our data. But you know, it's been a while since we haven't talked about feature scaling, so let me give you a quick recap of what it's doing here. So we are creating two objects, SCX and SCY here, that are objects from the standard scalar class that are going to scale your matrix of features x as well as your dependent variable y. And to scale x and y, we're applying the fit transform method from both the SCX and the SCY objects. And I guess the important thing to understand here is that you need to create two separate standard scalar objects because each of these two objects is going to be fitted to a certain matrix. So this one is going to be fitted to x and this one is going to be fitted to y, and therefore you couldn't create one object and apply it on both x and y. So that's why we're creating two, and we're not only doing some fitting but also doing some transforming, that is some scaling, and that's thanks to this transform component in the fit transform method. And basically this transform tool is what is going to scale x and y. Okay, so that was just a quick reminder and recap, and now let's actually re-execute this whole code to see if it was actually feature scaling that made this poor horizontal straight line model. Let's see. So I'm going to import the libraries first. Alright, done. Then import the dataset. Done as well. And now let's eventually apply feature scaling. So I'm going to select this section and execute. And here we get a little warning. And that's because, you know, our dataset was composed before of integers, and this is just a warning to tell that our data integers was converted into float, which is totally fine because by feature scaling our data, it's transforming of course the data into float. If we look at x right now, we have all these float numbers here that are the result of the feature scaling, and same for y here. Before we had the 10 levels from 1 to 10, and now we get those float numbers here from -1 to +2.7. Okay, so that's totally fine, and you know, warnings in Python happen all the time. Let's not worry about this, and let's move on to the next step. And the next step is to create our SVR regressor, and let's hope it will work fine. So I'm going to select this section, press Command and Control plus Enter to execute, and here we go. Regressor created properly with all the default parameters selected. Okay, so now we are about to find out if we get a better value than this 130k salary that we obtained when we didn't apply the feature scaling. So remember, this employee said that its previous salary was 160k. He's asking for more during the negotiation, and at the beginning of this tutorial we obtained 130k. But before getting the prediction itself, let's perhaps visualize the SVR result first, because we will immediately see if there is an error in our regressor, because you know, we will immediately see if we get this straight horizontal line. So let's do it. Let's actually select this section and execute to plot the SVR results. And much better now, much better than this straight horizontal line, right? Well, that is the SVR model itself. That is how it's trying to fit to the data. And we can see it's predicting each of the real observations very well now. Let's enlarge this. Okay, so just a reminder, the red points are the real observation points, that is the real salaries associated to the position levels, and all the points on this blue curve here are the prediction points. So for example, if we take this point here, that corresponds to a a rather large position level, so that's about the 8th position level, so that's, if I remember correctly, a senior partner. So for this level, the real observation point corresponds to this red point here and corresponds to this real salary, and the prediction point is actually the projection of this red point on the blue curve here, and that corresponds to this predicted salary. So don't worry about the scaled value here, we will get the real predicted salary, but it's just a reminder of how to make the distinction correctly between the real observation points and the predictions. But anyway, the point here is that the SVR is now fitting much better the data set, since the blue curve is getting very close to all the real observation points. But actually there is an exception. There is this exception for this real observation point here that corresponds to the CEO that, remember, has a $1 million annual salary and has a 10 level here. And can you figure out why the SVR is doing this? Well, the reason for that, the reason for the fact that this SVR model is not fitting to this real observation point corresponding to the CEO, well, it's because the CEO is considered as an outlier here. Sorry for the CEO, but that's what's happening. And the SVR model here is having some penalty parameters selected by default in its algorithm, and therefore, since the CEO observation point is quite far from the other data points, well, the SVR model considered this observation point as an outlier and made its fit on these observation points here. So that's why we get this very well fitted model for all these observation points, but not for the CEO. But that's actually okay for us, because what we're interested in is to predict the salary of this 6.5 level that is about here, because this corresponds to the previous level of this employee we're negotiating with right now. So it's all fine, and we can actually move on to the next step, prediction step, to actually see what this SVR model is predicting for our 6.5 salary of our future potential employee. So let's do this without waiting. We would love to directly select this and execute this, but unfortunately we have to do something here. And this little something that we have to do is of course related to the fact that we applied feature scaling to our data X and Y, and therefore our SVR regressor here is fitted to X and Y that were transformed. So since 6.5 is in some way not transformed, we actually need to transform it, and that's what we're going to do right now. So basically it's very simple. What we're going to do is to apply this SCX object, that is the object used to scale the features. Well, we're going to apply this object to 6.5 so that it can be suited to the regressor. So this won't be all, but let's start by doing this. So basically we're going to go into this predict function and here apply the SC_X scalar object, and then use the transform method again. So not the fit transform, because our object is already fitted to the matrix of features X, so that's fine. We just need the transform method. Here we go. And now we need to include this 6.5 in this transform method of the SCX scalar object. But be careful, there is a little something that we must be careful with. You know, it's always good to check the arguments of the function in case there might be a type issue. So you'll see what I mean. Let's press Command I to inspect the function. That's the transform method. And as you can see, this transform method is expecting X here, which is supposed to be an array. So this input here in the transform method must be an array. And this 6.5 value here is only a numerical value, so we will get a data type error if we leave only 6.5 here. We need to transform this 6.5 numerical value into an array. And to do this, the trick is really simple. We just need to use the numpy array, and we're going to create a simple array containing only one cell, which will contain this 6.5 numerical value. So to use this array function by numpy, we simply need to take numpy first with np, and then dot, and then array. Here we go. And now we need to open some new parentheses and then some brackets that will contain the 6.5 numerical value here. But if we only put some single brackets, this won't be an array, this will be a vector of one element. And so to create a real array, like a matrix, we need to put another pair of brackets, like this. Here we go. So basically what this means with the two pairs of brackets here is that it's an array of only one line and one column, that is one cell, containing this 6.5 numerical value. So now let's check to see if we have the right number of parentheses. Okay, so this parenthesis corresponds to array, this parenthesis corresponds to transform, so we just need to add one more parenthesis for predict. Okay, so that's better. Now, thanks to this transform method, the 6.5 numerical value is transformed in such a way that it is now fitted to the regressor. But unfortunately, that's not all. What we also need to do is to use the inverse transform to get the original scale of the salary. Because if we execute this line this way, we will get the scaled prediction of the salary, and we don't want that. We of course want the original scale of the salary. We don't want a prediction of 0.03 salary, because this is what we'll get with this line. You can try. So in order to get the original scale of the salary, we simply need to inverse the scale transformation, and to do this it's really simple. What we simply need to do is to apply the inverse transform method. And we need to apply this inverse transform method on a particular scalar object. So according to you, is it going to be the SCX object or the SCY object? Well, you know, since the result of this bit of code here is the prediction of the salary ypred, well, this corresponds to the dependent variable, and therefore the scalar object that we need to take to inverse the transformation is of course SCY. So let's do this. We're going to use SCY just to take the object, and then that's where we apply the inverse transform method, which is here. So here we go. And again, we need to put all this part here that, you know, gets our prediction, our scaled prediction of the 6.5 level salary. We need to put all this part in parenthesis because this is going to be the input of the inverse transform method of the SCY object. Okay, so now that's ready. Let's select this line and cross our fingers that we're going to get a good prediction of the salary. So let's go back to Variable Explorer to see. Let's select this line and execute. And here we go. We get a great prediction of $170,000. So that's a great prediction because first, we are quite close to the 160K salary mentioned by this potential future employee, and besides, it's on the right side of the negotiation. So the SVR is a great model. It just gave us a great prediction, and actually if you want to have a look at the real SVR fitting curve in a high resolution, well, we can do that very quickly. We can take this last code section here to get the smoother curve. So copy this and paste it here. Okay, so now we can specify that it's the SVR results. So let's do it. Let's have a look. Execute, and here it is. So that's the real SVR fitting curve, exactly like we had earlier, but we're getting a more beautiful and smoother curve. Conclusion, the SVR is a great model. We got a good prediction of our 6.5 level salary, and in the next section we're going to study the decision tree regression model. Let's see how they perform compared to what we've built so far. Until then, enjoy machine learning! Hello and welcome to this R tutorial. So today we're going to implement our second nonlinear regression model. It's going to be the SVR support vector for regression. So let's do it. We're going to use our regression template, and you're going to see how it's going to be so easy. So let's start by doing the basics. Set the right folder as working directory. So we'll go to Machine Learning AZ, Part 2 Regression, and then Support Vector Regression. Right, that's the right folder. Position salary CSV file. All good. Let's click on Set as working directory to set the folder as working directory. Great, and now we can start. So we're going to take our regression template, and we're going to take everything from here to here, copy, and paste it in our SVR model. Here we go, and now we just need to change a few things. So let's start by changing the basics. We're going to replace regression model here by SVR. Okay, and same here, SVR results. Okay, and same here. Alright, that was the easy step, and now let's get to the interesting step. So this interesting step is of course to create our SVR regressor, and we are creating it here. So I'm going to remove this, and now let's create this regressor. It's going to take 3 or 4 lines as usual. It's going to be very simple. We're going to use a function, which is the SVM function, very simply because the SVR, you know, is a support vector machine algorithm, but for regression. That's why we call it SVR. And therefore, we're just taking it from the SVM function, and you will understand why perfectly. So first, let's import the required package, because this function is contained in a package, which is the E1071 package. So let's go to our packages here and let's check if we have it. So I have it because of course I used it before, but you might not have it. So in case you don't have it, I'm going to type this line here that you will need to execute to install this package. So you type install that packages here, and then in the parenthesis and in quotes, you type the name of the package, which is E1071. Alright, and then you just select this line and execute, and this will install the package. I'm not going to do it because mine is already installed, and therefore I'm going to put that in comment. Just pressed Command plus Shift plus C. Alright. And now let's actually also add this line, library, and in parenthesis E1071, not in quotes. And this will select automatically the package here, E1071, because this will not always be selected. But by including that in your script, you will be all fine. This will always be selected. Okay? And now let's start creating our SVR regressor. So as usual, we're going to start by defining our regressor, and then equals. And then, as I mentioned before, we're going to use the SVM function, which is actually this, and then in parentheses. And now let's press here F1 to have a look at the arguments and see what we need to input. So the first argument is formula. So you start to know perfectly what it is. Of course, the formula is our dependent variable, which is, remember, salary, and then tilde. I just pressed Alt N, and then a dot here, and the dot specifies that we are taking all the independent variable of our data set. We actually have one independent variable, which is the level independent variable, so we could also type here level, but most of the time we use the dot because of course we have a lot more than one independent variable. But as a reminder, I'm taking one independent variable here so that we can clearly see the visual graphic results of the different nonlinear models that we're building. Okay, so now let's add the second argument. So I'm adding a comma here, and then next argument. So the next argument is data. Okay, I guess you know what this data argument will be. It's going to be, of course, our data set. Data set here, because we did not create any training set or test set. You know, before we used the training set here as the data, but here we don't have any training set, so of course we're going to take the whole data set because we want to make very accurate predictions. Okay, and now, finally, most important argument. Well, all the arguments are important, but the most relevant for this section about SVR is actually the next argument we are about to input. So this argument is actually not X or Y, these are optional arguments. The most important argument I was just talking about is this one, the type. Because this argument type will actually specify if you're making an SVM model, which is used for classification, or an SVR model, which is used for regression. So here, since we're building a nonlinear regression model, we will choose the EPS regression type. We could choose actually EPS regression or new regression, but as you can see, we want to take the most common one, the EPS regression. And if we were making an SVM model for classification, then we would have chosen C classification here. As you can see, C classification is the default type for classification. So in short, if you want to do regression, you choose type equals EPS regression. And if you want to do classification, you choose type equals C classification. And actually, in the next part about classification, we will make an SVM model. And for this specific model, we will choose the C classification type. Okay, but here we are doing regression, so we choose the EPS regression type. So let's input it. I'm going to type here type equals EPS regression. Alright, and you need to put that in quote, actually. Don't forget the quotes to prevent any error from happening. Okay, and that's actually the final argument. If you want, we can add the kernel argument here, just to specify that we want the Gaussian kernel, because here we're using a Gaussian kernel, but it's the kernel selected by default here, so we don't actually need to input it. But just keep that in mind, that we are here using the Gaussian kernel for our SVR model. Okay, but here we're all fine, and actually our model is ready to be created. So actually this is all we had to change in this regression template, and now we're ready to execute the sections one by one to create our model and find out about the final result and the final verdict, whether it's truth or bluff. So let's do it. I'm going to import the dataset first. Alright, here we go, well imported, we can have a look. So these are our dataset with the levels as the independent variable and the salaries as the dependent variable. Okay, great. And no need to split the dataset into the training set and the test set, no need for feature scaling because we're using the very popular E1071 library that includes it. And now let's create our model. So I'm going to select this whole section here, press Command and Control plus Enter to execute. Done, regressor created. Great. And now let's predict the new results. Would you like to start by visualizing the SVR results first or predicting the new result? Well, let's actually predict the result because this is the most exciting step, and let's keep the best for the end. But this step is actually very exciting also because we're getting the final prediction, we're getting the final predicted salary. So, you know, it's as you want. If you're doing actually this code by yourself before me, that's actually a very good exercise. So I really encourage you to do this. Choose whatever you want to execute first. It's ready anyway. You don't need to change anything more now. So I'm going to execute that right now. And actually we obtain a predicted salary of $177,000. Great. So remember, this employee who we are negotiating the future salary right now said that its previous salary was 160K, and our model predicted that its previous salary was 177K. So first of all, that's actually close to what this employee said, and besides, it's on the good side of the negotiation, so that's actually pretty good, and we can be satisfied with this result and our model. But to be really satisfied, let's see what's happening with the graphic results. So I'm going to execute this section, and let's have a look at the SVR model. And here it is. I'm going to zoom on it, and better. Okay, so first of all, this model fits very well most of the data points. As a reminder, the real observation points are the red points here, and all the points in this blue curve here, which is the SVR model itself, are the prediction points. So for example, if we're taking this red observation point here, well, the prediction is perfect because the prediction point is the projection of this red point on the blue curve. So it's actually the red point itself because the red point is on the blue curve. So that makes a perfect prediction. But here, for example, if we take a less accurate prediction but still a very good one, then we take the real observation point here, the red point, we project it on the blue curve, and that's the difference between the real salary and the predicted salary, which is here, if we project it back on the y-axis, which contains the salaries. But you can see that for all of these points, from this one to actually this one, the blue curve is actually getting very close to the real observation points, the red points, and so the predictions are very close to the real results. But that's for all these points of the data set, except for this one here. This one is left alone, which, by the way, corresponds to the CEO. So I'm sorry for the CEO, but the reason for what is happening here is that this is actually an outlier. Not to call the CEO an outlier, but this is an outlier because, as you can see, this point is actually far from the other points in terms of salaries. The CEO has a much higher salary than the previous positions. So for the SVR model, that's an outlier. And therefore, he actually didn't consider it. It's like it excluded this point in the model by not looking at it and making its predictions on these points here. So that's specifically due to the SVR algorithm itself, but there are a lot of parameters, and you can actually play with the parameters to change the way the SVR model perceives outliers. So for example, these parameters are the penalty parameters, the regularization parameters. It's most of the time well described in the description, and of course the E1071 library includes such techniques. But we're not going to do it here in this tutorial because we actually don't need to get a good prediction of the CEO salary. And remember, what we actually needed was a good prediction of the previous salary of this employee we're negotiating with. And this employee has a level 6.5. And around this point, we can see that the SVR model fits very well to our data set. And we actually get a prediction of 177K, quite close to the real or the mentioned salary of this employee, which is 160K. So that's actually pretty good, and therefore the verdict of truth or bluff according to our SVR model is rather truth. Okay, so not bad. The SVR made a good job here. Now let's see how decision tree regression and random forest regression will do. We'll see that in the next sections, so I'll see you there, and until then, enjoy machine learning.
Third, we will discuss about the decision tree regression and how to do it in practical way.
Hello and welcome back to the course on machine learning. In today's tutorial, we're talking about decision trees and the intuition behind them. Alright, so you may have heard the term CART, which stands for classification and regression trees. And this is an umbrella term that encompasses two types of decision trees, and as you've correctly guessed, they are the classification trees and regression trees. And in this course, we're going to talk about both types, but specifically in this section, we're focusing on the regression trees. And I wanted to mention right away that regression trees are a bit more complex than classification trees, and that's why this tutorial is going to be a bit longer and it's going to require some additional attention. But nevertheless, we're still going to break this kind of somewhat complex topic into very simple, bite-sized elements of information, so it will all make sense, and towards the end of it, you'll be quite comfortable with regression trees. So let's get straight into it. Alright, so here we've got a scatter plot which represents our dataset, so a dataset that has been given to us. And the interesting thing about this scatter plot is that we've got two independent variables, x1 and x2, and what we're predicting is a third variable, a dependent variable, which is y. And you cannot actually see y on this chart, and that is because this is simply a two-dimensional chart. You can only fit the two variables. Y is the third dimension, and if you think about it, it's like sticking out of your screen. That's where that dimension is, and this is just a projection of all the points on the x1, x2 plane. And so if I add the third dimension, it would look something like that. But once again, we can't see y right now. And the interesting thing is that we don't actually need to see y, because we need to work with this scatter plot first for a little bit to build our decision tree, and then once we've built it, we'll return to y. Now, a quick point I wanted to make here is that I've seen decision trees explained with just one independent variable, so x1 or just x and y, and in that case, yes, you can just put x1 over here, and then y would go over here, and you would have a bit of a different kind of diagram, and you'd be able to explain it that way. But at the same time, I think it might not really drive the point home, and it can be a bit confusing when it's explained like that, although sometimes it is done. Nevertheless, I thought we'd go the full way, we'd do the full Monty, and we'd look at this problem with two independent variables, because it'll be a more robust explanation. So it will make it a bit more complex, but it's definitely worth it in the long run, because that way we'll understand the decision tree regression a bit, or actually I would say quite a bit better. Alright, so let's continue. We've got the x1 and x2, these are independent variables. The dependent variable, we cannot see it, it's the third dimension, and we're actually going to forget about it for a little while, right? So we're going to just forget about it, because we need to work with this scatter plot to see how our decision tree is going to be created. So once you run the regression tree or decision tree algorithm in the regression sense of it, what will happen is your scatter plot will be split up into segments, and let's have a look at how an algorithm could go about doing that. So an algorithm would create a split over here, for example, at somewhere around 20, so it would basically split your diagram or your scatter plot into two parts: everything that's less than 20, everything that's greater than 20 for the x1 variable. Then another split would happen here, so for all of the elements in this side, they would be compared to 170, greater or less. Then there would be another split here, and then maybe another split over here. Now, how and where these splits are conducted is determined by the algorithm, and it involves looking at something called the information entropy, and it is a mathematical concept. It is quite complex. So it basically means when I perform this split, right, is this split increasing the amount of information that we have about our points? Is it actually adding some value to our way that we want to group our points? And the algorithm knows when to stop is when there's a certain minimum for the information that needs to be added, and once it cannot add any more information to our setup by splitting these leaves. They're called leaves, so each one of these splits is called a leaf. By splitting these leaves, once it can't add any more information, then it stops, or the algorithm could, let's say, stop when you have less than 5% if you were to conduct a split, then you would have less than 5% of your total points in that leaf, and then that leaf wouldn't be created. So there are different variations or different options for that to happen. But like the most important thing is, of course, where the splits are happening. And if you'd like to learn more about that, you'd need to study a bit more about information entropy. We're not going to go into that mathematical depth right now. For us, it's sufficient to know that the algorithm can handle this, and that it is finding the optimal splits of our data set into these leaves, and the final leaves are called terminal leaves. And then we're going to focus on the practical application of this algorithm, how and why we're using these decision trees, and how this regression is going to work. All right, so hopefully we're on the same page. Let's continue. So we're going to rewind all of this a little bit, and we're going to create these splits one by one, and alongside we're going to actually start drawing our decision tree. So there's our diagram, brand new and fresh, and there goes our first split. So now we're going to start creating our decision tree. The split happened at 20, so let's start drawing. There is our first decision, and we have two options, yes and no. All right, so let's see what happens next. Next happens split 2. Split 2 happens at 170, and only happens for the points that are greater than 20. So that means you would check this condition, x1 is less than 20, meaning you check no, the answer is no, and then you check if x2 is less than 170. x2 is less than 170. Then a split 3 happens on the other side, and it checks if x2 is less than 200. Let's add that here, x2 is less than 200. And then split 4 happens at 40, and it checks if x1 is greater or less than 40. And split 4 only happens for the points that answered to split 1. They answered no, it's not less than 20, and to split 2 they answered no, it's yes, it's actually less than 170. So no, it's not less than 20, yes, it's less than 170, and then this is where split 4 happens. x1 is less than 40, yes, no. All right, so that's our decision tree. It's done, it's drawn. And so what happens next? What do we actually populate into those boxes? Well, this is where we need to remember about our dependent variable, the third dimension. And what we need to check here is, how are we going to predict the value of y for a new observation that gets added to our scatter plot or to our data set? So let's say we add a observation which has x1 equals to 30 and x2 equals to 50. It would fall somewhere over here, and 50 is somewhere over here. It would fall somewhere over here. So obviously it falls into this terminal leaf. And how does that information, so as you can see, by adding these splits, we've added information into our system. So how does that information, that now we know that it falls into this terminal leaf, how does that information help us in terms of predicting the value of y for that new element that we're going to add? Well, the way it works is, it's actually pretty straightforward. The way it works is you just take the averages of each of your terminal leaves. So you take the average of y for all of these points, and that will be the value that will be assigned to any new point that falls in this terminal leaf. Same for this terminal leaf, same for this terminal leaf, same for this one, and same for this one. So let's have a look. Let's say the average for y here is 65.7, the average for y here is 300.5, 1023 here, minus 64.1, 0.7 here. So for that point that we just discussed with x1 equals 30 and x2 equals 50, the predicted value of y, the regression tree algorithm, would predict a value of minus 64.1. If it were to fall in any other terminal leaf, then that's what the value there would predict. So as you can see, it's actually pretty straightforward. It's very simple. It's just taking averages. But you do need to remember that we are working, the whole point of this exercise is to add more information into our chart, into our system, to better predict y. Because if you think about it, what was our other option? What is our default option? If the default option without running any machine learning on this data set is to just take all of the points and take the average across all of the points, and whatever that is, wherever our new point, the new element of data that is added to our data set, wherever it falls, we just assign it always that average for all of the points that we had existing previously. What we did now is we've split our diagram up into these terminal leaves. The machine learning algorithm has added information into our system, and so now we can more accurately predict the value or assign the value of y to a new coming element. And as you can see, now it's the average, not just across all of them. The average is taken in specific parts or segments of our scatter plot, and therefore it is, or it's supposed to be, more accurate. That's the whole point of the regression tree. And now the last thing we have left to do is to add the values into our decision tree. So basically we just add those values in here, and now whenever we have a new value, what would happen is the algorithm would just go through these checks, and it would check where it falls and it would assign the value, and that's pretty much it. So the scatter plot is more for like visualization, conceptual purposes, so you can maybe drive some insights from there, but the core of decision tree is actually held here, and that's why the algorithm is called a regression tree. I hope you enjoyed today's tutorial, and hopefully we did break down this quite complex topic into some simple and actionable steps, and I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k-nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k-nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder, we're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k-nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k-nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. So in the previous sections we already introduced two nonlinear regression models, the polynomial regression model and the SVR regression model. So far polynomial regression seemed to be the best one, and today in this tutorial we are going to build the decision tree regression model and see how it will handle the problem. Okay, so let's quickly take care of the basics. We'll go to File Explorer here to set the right folder as working directory. So here we need to go to Regression, and we are now in the Decision Tree Regression section. So let's go on it, make sure that we have the position salary CSV file. And if that's the case, let's click on this little button here to set this folder as working directory. And now let's start to build our decision tree regression model. So we'll go to our regression template and take everything from here to here and paste it here. Now let's change the basics. Here I'm going to call that decision tree regression. Alright, let's copy that and let's paste it here. Alright, and now the basics is done. We are ready to change. The only thing that we do need to change, this part here where we create our regressor. So let's remove this comment and let's now create our regressor. So as usual, it's going to be very simple. It's going to take 3 lines, and we're going to do exactly like before. We're first going to import a class from a certain library, and then we're going to create an object of this class, which will be our regressor object, our decision tree regressor. And then we will use the fit method on this regressor object to fit our regressor to our dataset. And then it'll be ready. We will just need to execute the sections one by one, and we will get to the final results. So let's do it. Let's start with the first step here, which is to import the right class for the job. So actually this class is from the sklearn.tree library. All right. And from this library, we are going to import the decision tree regressor. So careful to use the capital here, capital D, capital T, and capital R. That's because it's a class, and this is the name of the class. So as usual, a very intuitive name. Alright, so we imported the class, and now let's create an object of this class, which is our regressor object. So we're going to call it regressor as usual, and then equal, and then we're going to call the class that we just imported, because this is actually an object of this class. Here we go, and of course we add some parentheses because we need to specify some arguments. So let's have a look at these arguments. Let's press Command or Control plus I to inspect the decision tree regressor class. And what do we have here? Okay, so we have the criterion, and the default criterion is MSE, mean squared error. So you know we're taking the square difference between the prediction and the real result, and we're taking the sum of these differences to measure the error. So this is a very good and common criterion, and this is the one we're going to use for our decision tree regressor object. And since it's the default here, we don't have to do anything, we're fine. And then we have some other parameters like splitter or max features. That's if you want to take a more advanced approach of how you build your decision tree. So we will not focus on that right now. We will leave it to the default parameters. Actually, the default parameter for splitter is, as you can see, best. So I guess we're fine with that. And so we will just actually, you see there are a lot of parameters, so we're not going to input some values one by one, but we are going to specify a random state value because we all want to get the same results. Okay, so let's do it. Let's input here random state equals, so we can pick whatever number we want. I usually input 0 or 42. Well, let's put 0 here. Okay, great, and now we'll all get the same result. So we are on the same page. So that was the second step, creating the regressor object from the decision tree regressor class. And now the final step is to fit this regressor object to our dataset. And as usual, we're taking our regressor object like this, then a dot because we're calling a method, and then we're taking the fit method here, right? And now we need to add some parentheses because it has some arguments, and as you can see, those arguments are x and y. X is our matrix of features, and y is our dependent variable vector. And that fits our regressor object to our dataset because our dataset is composed of x, the matrix of features, and y, the dependent variable vector. Okay, great. And now we are actually ready to execute the sections one by one and get the final result. So let's do this. So remember, for SVR we had to apply feature scaling. This was a trap. Let's see if it's still a trap here. Let's see if we need to apply it. We will first try not to execute the whole thing without applying feature scaling, and we'll see what happens. Okay, so let's execute the section one by one. Let's import the libraries first. done. Let's import the data set and select the right columns. Alright, done. Now no need to split the data set into the training set and the test set because we have a very small data set. No need to apply feature scaling maybe. And now we're finally getting to the section where we create our decision tree regression. So let's select the section and execute to really create it. Here we go, create it properly, and all the default parameters were selected. Okay, so far so good. And now let's either predict the previous salary of this employee that had a 6.5 level in its previous company, or visualize the results. Well, let's keep the best for the end and let's see what is our prediction for this previous salary. So remember, we're negotiating with a future potential employee that is about to be hired. We're negotiating its offer. This person is saying that its previous salary was 160k and he's asking for more, and based on the information we have on the table of salaries of the previous company and knowing the information that this employee had a level 6.5, we are trying to predict its previous salary. So this person is saying its previous salary was 160k. Let's see what our model says. Alright, so the prediction is made. Now let's see what it is. We need to go to Variable Explorer, and it's 150k. Wow, for the first time we are getting a prediction below the mentioned salary. Well, for polynomial regression it was very slightly below. It was 158k, and now we get 10k less than what this person was saying as its previous salary. But I guess it's quite close, and that's still a good prediction. Even if it's not on the good side of the negotiation, I guess that's fine. So let's check to see what happens on the plot, where we can see the decision tree regression results. So we're going to execute this section and find out about how the decision tree regression model handled the dataset and managed to fit its model to our dataset. So let's do this, and here's the plot. Wow, okay, so I'm going to enlarge this. And now, the first word I have to say here is trap, or red flag. Right now, we're just in front of a new trap. According to what Kirill explained in the intuition tutorial, do you think that's the real shape of a decision tree regression model? Well, because you know what Kirill explained is the algorithm of decision tree regression is that by considering the entropy and the information gain, it's splitting the independent variables into several intervals. So in the intuition tutorial you had two independent variables, so the different intervals formed some rectangles in which you took the average of the dependent variable values. But here, since we are in one dimension, that means that the algorithm will only take intervals here of the independent variable. For example, that should be one interval, and here it looks like it's a second one, and here it's the third one, and here a fourth one. Okay, but as you understood in the intuition tutorial, it's taking the average in each interval. So if it's taking the average, how do you want to have this straight line here that is not horizontal? Because you know what the decision tree regression is doing is that in each interval it's calculating the average of the dependent variable salaries, and therefore for all the levels contained in this interval, the value of the prediction should be a constant equal to this average of the dependent variable in this interval. And here, as we can see, it's not a constant. You know, the prediction here is not the same as the prediction here. So either it's considering an infinity of intervals with different constants in each of those infinite intervals, or either we have a problem here. Of course, it's not the first option. Of course, the decision tree regression is not considering an infinity of intervals between this level and this level. So it's definitely the second option. So now do you see where the problem comes from? Well, the answer is in our regression template, because what we observe here is only due to the resolution we picked to plot these decision tree regression results. Because we're actually plotting the predictions for each of the 10 levels incremented by 1. That means that here, you know, it's only plotting the predictions of the 10 salaries corresponding to the 10 levels, and then it's joining the predictions by a straight line here because it had no predictions to plot in this interval here of the independent variable level. And the fact that it's a problem for this new nonlinear regression model, the decision tree model, is due to a very specific reason. For the previous nonlinear regression models, we could use the code that generated this plot because the models were actually continuous. So for example, in the polynomial regression model, well, between these prediction and these prediction, well, it was actually almost a straight line here. However, right now we are facing a new kind of regression model. Remember, the first kind of regression model we studied was the linear regression model. Then the second kind of regression model we saw was the nonlinear regression model, and now we're facing a new kind of regression model. It's the nonlinear and non-continuous regression model. Indeed, all the previous regression models that we saw, whether they were linear or not linear, they were all continuous. But here, the decision tree regression model is not continuous, and this is the first non-continuous machine learning model we are seeing together. And so, do you know what is the best way to visualize a non-continuous regression model? Well, as I was telling you, the answer, the solution for this is in our regression template. So let's have a look, and actually we need to take the code section that visualize the regression model results in higher resolution. So let's take this and let's actually go back to our decision tree regression file and replace this code here, because this is totally not appropriate for a decision tree regression model because it's a non-continuous model, and so we need to replace this code by the same but for the higher resolution. And now let's check it out. The model is actually ready. We can actually replace that by decision tree regression. And now let's check it out, and you will see what the real decision tree regression model looks like in 1D. So let's do it. Let's select all this and execute. And here it is. That's what it looks like. And actually, since it's a non-continuous model, we should even have some strictly vertical line here, to represent better the non-continuity. And to do this, we just need to increase the resolution. So I'm going to put 0.01, and you'll see that we'll get the real representation of the decision tree regression results. So let's do it. Here it is, now almost vertical, and that's a clear representation of the decision tree regression model. So now let's zoom on it, and now it makes much more sense. Because as Kirill explained, based on the entropy and the information gain, it splits the whole range of your independent variable into different intervals. So here we can clearly see what the intervals are, and as Kirill explained in the intuition tutorial, the decision tree regression model is considering the average of the dependent variable values in each of the intervals. So for example, if we consider this interval here, the average of the salaries in this interval, well, that's very simple. It's actually 150,000. And so for each of the level between 5.5 and 6.5, the salaries will be predicted to be $150,000. So we already know what our model will predict for our 6.5 level here. It's going to predict 150K. So speaking of this prediction, and now that we get the decision tree regression graphic results very well, let's actually check that the previous salary of this employee that had a 6.5 level in its previous company is really 150K. Let's check it out. Let's select this line and execute, and here it is, 150,000. So now I just want to say two things to conclude. The decision tree regression model is not an interesting model in 1D, but it can be a very interesting and very powerful model in more dimensions. So that's why you can use this code here for your dataset. You have the code here that builds the model, and this one here that makes the prediction, but then you won't be able to use this code because you'll have probably a lot of independent variables and therefore a lot of dimensions. But Kirill gave you the explanation in 2D, I'm giving you the explanation of 1D so that now in your mind, you can perfectly represent in your head the decision tree regression and how it works. And now I would like to end this tutorial by an enigma. In the next section you will see random forests. And a random forest is actually really simple. It's just a team of several decision trees. So, knowing that this is the result of one tree, what do you think we'll get with a team of 10 trees? Or even 100 trees? Or 500 trees? The first question is, do you think we'll get this shape of some stairs here? And the second question is, do you think we'll get a much more accurate prediction, like a prediction that is getting very close to the 160K that is supposed to be the real salary? So these are the two questions. I will let you think about that, and I look forward to giving you the solution in the next section. Until then, enjoy machine learning! Hello and welcome to this R tutorial. In the previous sections we already introduced two nonlinear regression models, the polynomial regression model and the SVR regression model, and today we're going to introduce a new nonlinear regression model, which is the decision tree regression model. So far, the best model we had for our dataset and our specific problem was the polynomial regression model. Let's see how decision tree regression will do and compare it to the previous ones. So let's start with the basics. Let's set the right folder as working directory. So right now I'm going to the regression folder, and we are now in decision tree regression. Almost getting to the end. So this is the right folder containing the position salary CSV file, make sure of that, and click on this more button here and set as working directory. All good. And now let's take our regression template to build this model efficiently. So we take everything from here to here and pasting it here. Right. And now we just need to change a few things. So let's change the basics. Let's replace here regression model by decision tree regression. Alright, I'm gonna copy that and put that same title here. Alright, visualizing the decision tree regression results, and same here. Alright, and now let's change the most important thing, which is the part where we create our regressor. So I'm gonna remove that comment line here, and now let's build our decision tree regression model. So it's gonna be the same thing as any time. We're gonna import a package and then use a function from this package to build our regressor. So this package for decision tree regression in R will be the rpart package. For those of you who don't have the rpart package in your packages here, I will type this command line so that you can install it. So as you can see, mine is already here, rpart. Just check if you have it, and if you don't have it, just type here install.packages, and then in the parentheses in quotes, you type the name of the package, which is rpart. Alright, and then you just select this line, execute, and this will install the package. Alright, but I'm going to put this line as comment. Just press Command plus Shift plus C. And now let's also add this line library, and then parenthesis, the name of the package we want to select, well, import, rpart, right? And as you can see, rpart is not selected here. And when this line of code will be executed, then this will be selected here. Alright, and now we are ready to start building the model. So as I just said, we're going to take a function from this rpart library, and this function is actually rpart as well. So let's use this function, and as usual, we're going to call a regressor. So here it is. So that's our decision tree regression regressor. And let's now use the rpart function. Alright, so now let's see what arguments we need to input. The best way to do that is to press F1 here so that we get the info about the rpart library. So usually we have it here, but now we just need to click on this link here, and that will give us info about this rpart library. Okay, so let's see what we have. The first argument is formula. So you know what to do here. We just need to write formula equals the dependent variable, then a tilde, and then a dot that represents all your independent variables. Alright, but that we know perfectly. Then data. So data is the data set on which we want to build our decision tree regression model. So since we did not build any training set, data is going to be the data set, exactly like polynomial regression and SVR regression. Alright. Then weights is an optional argument. You can add some weights to make your model more advanced, but you know, this is more advanced, so we will not cover that right now. And then you have some other arguments that are optional, but that can help you make your model even more robust, or you know, include some regularization techniques or penalization to prevent overfitting, that sort of things. But right now we just want to build a simple decision tree regression model because we have a simple data set, and so we only need formula and data. So let's go back to R and let's input these arguments. So the first argument was formula. And then, as I mentioned, it's formula equals salary because it's our dependent variable. Then tilde, just pressing Alt N here. And then a dot, or actually level. But, you know, I want to make this script that can be also applied to your datasets, so I'll use a dot. Alright, so that's the first argument. And now let's give the second one. The second one was data. So data equals dataset. And now our regressor is ready to be built. Only with these two arguments, very simple, let's do it. So it's ready to be built, and that means all our code is ready to be executed because we don't need to change anything more. So let's execute the sections one by one, and let's see what happens with decision tree regression. So I'm going to select the first section, execute, dataset 1 imported. Here it is. So the independent variable contains 10 levels here. and the dependent variable contain the 10 salaries here associated to these 10 levels here, and our goal is to predict the salary of a 6.5 level. The data is not linearly distributed, this is not a linear problem, so that's why we're making some nonlinear regression models to make this prediction. Alright, so then no need to split the dataset into a training set and a test set, because as you can see, this is a very small data set. Then no need for feature scaling, because for decision trees, we don't need to do any feature scaling because the way this model is built is based on conditions on the independent variable and not on Euclidean distances. So we're fine with that. We definitely don't need to apply feature scaling, and we can move on to the next step, which is to create our model. So let's create it. Executing. Alright, perfect. Regressor is created. And now let's get our final verdict. Okay, so 160k according to this person, and now let's see the predicted salary according to our model. So executing this, and we get a $249,000. Wow, much higher than the salary mentioned by this person. But let's not drop hasty conclusions, and let's see what's happening on the graph here. So I'm going to select all this, and let's see what's happening with the decision tree regression results. Alright, that's what I thought. Okay, so we don't need to zoom on it, we clearly see what's happening here. It's plotting a straight horizontal line, exactly like we saw in SVR, but for Python. For those of you who didn't follow the Python tutorial, know that we already encountered this situation when we get a straight horizontal line. And actually in SVR, this was due to the fact that we didn't apply feature scaling to our dataset. So what do you think the problem is here? Do you think it's due to the fact that we didn't apply feature scaling like for SVR, and we need to apply feature scaling to get a model fitting properly the dataset? Well, as I mentioned in the beginning of this tutorial, we definitely don't need to apply feature scaling for decision trees, because decision tree regression models are based on conditions on the independent variables that has nothing to do with Euclidean distances. And you know, when we need to apply feature scaling, it's because the machine learning models are based on Euclidean distances, and we need to put all the independent variables on the same scale so that one independent variable is not dominating another one. But this is not the problem here. This is not about feature scaling. You can try to apply feature scaling here and re-execute this, but you'll get the same problem of a straight horizontal line. And of course, this is actually the decision tree model. This is actually one model of decision tree, but this is of course not the best version of decision tree regression we want to get. So can you start seeing what's the problem here? And especially after watching the intuition tutorial made by Kirill, can you spot the problem? Okay, I'm going to tell you this problem is related to the number of splits. Because, you know, the way the decision tree regression model is made is that it's making some splits based on different conditions. So the more conditions you have on your independent variables, the more you have splits. And here, we clearly have no split here because, you know, all the predictions are equal to $250,000. So, you know, it took all the different salaries for the different 10 levels here and made an average and just gave the average for all the levels. So no conditions here, no split, and therefore that's absolutely not interesting, especially for the potential that decision tree can have. So what we'll do now is add a parameter here that will set a condition on the splits. You know, that's what I was telling you. We have several parameters in this RPAR library, and we can use these optional parameters to improve our model and make it more robust. Well, this is exactly what we're going to do now. We are going to get back to RPAR, so I'm going to press F1 here. Oh, actually this time RPAR is showing up. Okay, so great, RPAR is here, and as I mentioned, RPAR has several parameters that we can use to make our model more robust. And the one we're interested in right now is one parameter that will correct this problem we had with the splits. So this parameter is actually the control parameter. And right now I'm going to give you a little trick to solve this problem on the splits we had just obtained here. So I'm going to add this third optional argument, you know, to improve our model. Right now we're doing some model performance improvement, so that's a thing that machine learning scientists do very often in their job. So don't worry, we'll get more advanced sections on it, especially when we cover cross-validations to find the best models, selecting the best parameters. But here we will just do some simple model performance improvement, and we'll just add this control parameter, and then I'm going to give you this little trick. So this little trick is to take the rpart library again. So we're taking rpart control here, which is a function, and in this function we're going to add an argument. As you can see here on this yellow rectangle here, we have the first argument that is min split, and that's exactly what we're interested in, and that's what will solve our problem. Because, you know, actually we didn't have any split here because it just took the average, so it's like we had no conditions on the independent variables, so no splits. So to make sure we have some splits and some conditions on the independent variables, we will actually set min split to 1, and that will solve the problem. So let's try. Let's now reselect this section to create a new regressor. So rpart is already imported, so I don't need to select that again. And let's create this new regressor. Okay, done. Perfect. New regressor created, all properly. Okay, and now let's perhaps first visualize the results to see if our model is now correct before getting to the final verdict, because, you know, we need to validate the model now. So I'm selecting this section, and let's see what we get. Let's cross our fingers. Here we go. I'm going to zoom on the plot. And now the first word I have to say here is trap or red flag. Right now we're just in front of a new trap. The model is improved. Definitely, we can definitely see that we have more than one split here. For example, here that's a split, that's another split here and here. So okay, we solved the problem of the number of splits. But according to what Kirill explained in the intuition tutorial, do you think that's the real shape of a decision tree regression model? Well, because you know what Kirill explained is the algorithm of decision tree regression is that by considering the entropy and the information gain, it's splitting the independent variables into several intervals. So in the intuition tutorial you had 2 independent variables, so the different intervals form some rectangles in which you took the average of the dependent variable values. But here, since we are in 1 dimension, that means that the algorithm will only take intervals here of the independent variable. For example, that should be 1 interval, and here it looks like it's a second one, and here it's the third one, and here a fourth one. Okay, so basically it looks like we have 4 conditions and 4 intervals that are making the splits, but as you understood in the intuition tutorial, it's taking the average in each interval. So if it's taking the average, how do you want to have this straight line here that is not horizontal? Because you know what the decision tree regression is doing is that in each interval it's calculating the average of the dependent variable salaries, and therefore for all the levels contained in this interval, the value of the prediction should be a constant equal to this average of the dependent variable in this interval. And here, as we can see, it's not a constant. You know, the prediction here is not the same as the prediction here. So either it's considering an infinity of intervals with different constants in each of those infinite intervals, or either we have a problem here. Of course, it's not the first option. Of course, the decision tree regression is not considering an infinity of intervals between this level and this level. So it's definitely the second option. So now do you see where the problem comes from? Well, the answer is in our regression template, because what we observe here is only due to the resolution we picked to plot these decision tree regression results. Because we're actually plotting the predictions for each of the 10 levels incremented by 1. That means that here, you know, it's only plotting the predictions of the 10 salaries corresponding to the 10 levels, and then it's joining the predictions by a straight line here because it had no predictions to plot in this interval here of the independent variable level. And the fact that it's a problem for this new nonlinear regression model, the decision tree model, is due to a very specific reason. For the previous nonlinear regression models, we could use the code that generated this plot because the models were actually continuous. So for example, in the polynomial regression model, well, between these prediction and these prediction, well, it was actually almost a straight line here. However, right now we're facing a new kind of regression model. Remember, the first kind of regression model we studied was the linear regression model. Then the second kind of regression model we saw was the nonlinear regression model. And now we're facing a new kind of regression model. It's the nonlinear and non-continuous regression model. Indeed, all the previous regression models that we saw, whether they were linear or not linear, they were all continuous. But here, the decision tree regression model is not continuous, and this is the first non-continuous machine learning model we are seeing together. And so do you know what is the best way to visualize a non-continuous regression model? Well, as I was telling you, the answer, the solution for this is in our regression template. So let's have a look, and actually we need to take the code section that visualize the regression model results in higher resolution. So let's take this and let's actually go back to our decision tree regression file and replace this code here, because this is totally not appropriate for a decision tree regression model because it's a non-continuous model, and so we need to replace this code by the same but for the high resolution. And now let's check it out. The model is actually ready. We can actually replace that by decision tree regression. And now let's check it out, and you will see what the real decision tree regression model looks like in 1D. So let's do it. Let's select all this and execute. And here it is. That's what it looks like. And actually, since it's a non-continuous model, we should even have some strictly vertical line here, you know, to represent better the non-continuity. And to do this, we just need to increase the resolution. So I'm going to put 0.01, and you'll see that we'll get the real representation of the decision tree regression results. So let's do it. Here it is, now almost vertical, and that's a clear representation of the decision tree regression model. So now let's zoom on it, and now it makes much more sense. Because, as Kirill explained, based on the entropy and the information gain, it splits the whole range of your independent variable into different intervals. So here we can clearly see what the intervals are. The first interval is from 1 to 6.5. The second interval is from 6.5 to 8.5. Then the third interval is from 8.5 to 9.5. And finally, the last interval is from 9.5 to 10. So there we go, we can clearly see the intervals now. And as Kirill explained in the intuition tutorial, the decision tree regression model is considering the average of the dependent variable values in each of the intervals, this one, this one, this one, and this one. So for example, if we consider this interval here, the average of the salaries in this interval, well, that's very simple, it's actually 250,000. And so for each of the level between 6.5 and 8.5, the salaries will be predicted to be $250,000. So we already know what our model will predict for our 6.5 level here. It's going to predict 250K. So speaking of this prediction, and now that we get the decision tree regression graphic results very well, let's actually check that the previous salary of this employee that had a 6.5 level in its previous company is actually 250K. Let's check it out. Let's select this line and execute, and here it is, 250,000. Exactly like we predicted, because we can clearly see that on this plot. So now I just want to say two things to conclude. The decision tree regression model is not an interesting model in 1D, but it can be a very interesting and very powerful model in more dimensions. So that's why you can use this code here for your dataset. You have the code here that builds the model, and this one here that makes the prediction, but then you won't be able to use this code because you'll have probably a lot of independent variables and therefore a lot of dimensions. But you know, Kirill gave you the explanation in 2D, I'm giving you the explanation of 1D so that now in your mind, you can perfectly represent in your head the decision tree regression and how it works. And now I would like to end this tutorial by an enigma. In the next section you will see random forests. And a random forest is actually really simple. It's just a team of several decision trees. So, knowing that this is the result of one tree, what do you think we'll get with a team of 10 trees? Or even 100 trees? Or 500 trees? The first question is, do you think we'll get this shape of some stairs here? And the second question is, do you think we'll get a much more accurate prediction, like a prediction that is getting very close to the 160K that is supposed to be the real salary? So these are the two questions. I will let you think about that, and I look forward to giving you the solution in the next section. Until then, enjoy machine learning.
Fourth, we will discuss about the random forest regression and how to do it in practical way.
Hello and welcome back to the course on machine learning. Today we're talking about the random forest and the intuition behind it. And specifically we're going to be talking about the random forest applied to regression trees rather than classification trees this time. But the concept is very similar, and you'll find that this tutorial is very similar to the one for the random forest on classification trees. Alright, so random forest and ensemble learning. Ensemble learning, so random forest is a version of ensemble learning. You've got other versions such as gradient boosting, and ensemble learning is when you take multiple algorithms or the same algorithm multiple times and you put them together to make something much more powerful than the original. And let's see how this works. So you pick a random k data points from your training set. So now we're kind of going to leverage a lot what we talked about in the section on regression trees. So you remember there we had lots of data points, and then we built a regression tree, and or we built a decision tree and used that to forecast the value that would be assigned, or the y value for any new element that would be added to our data set as the average in the terminal leaves, basically. So here what we're doing is we're using the whole data set we had, and we're only picking k data points from that training set. Then we're going to build a decision tree associated to these k data points. Rather than building a decision tree based on everything in your data set, you're just building a decision tree based on those data points that you select, so a subset of your data set. Then you choose the number of trees that you want to build, and you repeat steps 1 and 2. So you just keep building and building and building these trees. So you're building a lot of regression decision trees. And then finally, you're going to use all of them to predict. So for a new data point, make each one of your entries predict the value of y for the data point in question, and assign the new data point the average across all of the predicted y values. So basically, instead of just getting one prediction, you're getting lots of predictions. By default, usually these algorithms are set to about 500 trees at least. So you're getting 500 predictions for the value of y, and then you're taking the average across those. And in that way, you're not just predicting based on one tree, but predicting based on a forest of trees, and that improves the accuracy of your prediction, because it is you're taking the average of many predictions, and therefore even if one is for instance somehow one of the decision trees was built exactly perfectly because the way of those data points were selected, so just didn't turn out as a perfect tree or a great tree even. If you were using it by itself, you'd get a bad prediction. But because you're using the average, it is less likely, so you're going to get a more accurate prediction. And the second thing is that they're more stable. Algorithms like this, ensemble algorithms, are more stable because any changes in your data set could really impact one tree, but for them to really impact a forest of trees, it's much harder. So therefore, ensemble is much more powerful in that way. And what this reminds me of is the game that is often played at fairs or parties and things like that, where you have a jar, and inside this jar there's lots and lots of, for instance, jelly beans, or it could be marbles, or there could be like a huge net with balloons inside it. And we have one in the mall sometimes where there's lots of balloons inside a net in the ceiling, and you need to guess how many balloons there are, and whoever guesses will get like a car, can win a car. And so it's like a crazy prize for just guessing number of balloons. And although this is not an example of specifically a random forest, a regression random forest method, it's still an example of an ensemble type of method. So the best way, or one of the ways to beat that game when you need to guess a number of marbles in a jar, for instance, is not to actually go and guess, but it's actually to get a pen and a paper and stand next to the person that's holding this jar or that's conducting this event, and you just stand next to them, and then you wait for other people to come and guess. Every time somebody guesses, you just ask them, as soon as they're like guessed and they're walking away, you ask them, hey, because usually they write down their number and they put it inside a like an envelope or something, and then the winner is announced later on. So they don't know whether they guessed right or wrong, but regardless of that, they're walking away, and you just ask them, hey, what number did you guess? And you just write down their number. And then the next person guesses, and you write their number down, and you write their number, and you keep writing the numbers down, and you just keep doing that until you have like a substantial number of entries, maybe 100, or maybe if it's a very popular contest and people are guessing like crazy, like attempting the guessing, then you might even get like couple of hundred, or even if you're very determined, you might get 1,000 of entries over a couple of days. And then what you do is you just average them out. Or if you don't want, maybe you take the median. If you don't want outliers, like people just guessing random numbers like 1 or 5 million, so you don't want them to affect, or you just take the outliers out and then you average out. Anyway, you either average it out or you take the median, and statistically speaking, you have a much higher likelihood of being closer to the truth if you take the average of people, because people are natural beings and their kind of visual perception will be most likely normally distributed, and therefore once you hit the middle of that normal distribution, you are more likely to be on the money than any one of them. And that's a pretty cool concept. That's an example of an ensemble method where you're taking, instead of just throwing that guess by yourself or taking the guess of one individual person, you're averaging out across multiple guesses, and you're more likely to be the closest one to the truth. And if the prize is given not just to the person that gets spot on, but to the person that guesses closest to the truth, then you've got yourself a very powerful advantage using data science. So if you have the patience and determination, then try it out next time you see one of these games and see how you go. Would love to hear back from you, because I never have the patience to stand there and just count. But it is a statistical approach to a challenge like that. So hopefully you enjoyed today's tutorial. I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. So here we are at the final round of regression with our last nonlinear regression model, which is the random forest regression. In the previous section we saw the decision tree regression model, so if now the decision tree regression doesn't have any secret for you, then you will perfectly understand random forest regression. Because a random forest is just a team of decision trees, each one making some prediction of your dependent variable, and the ultimate prediction of the random forest itself is simply the average of the different predictions of all the different trees in the forest. And speaking of that, at the end of the last section about decision trees, I asked you an enigma. What do you think we'll get in terms of prediction and in terms of visualization? Do you think we'll get the shape of some stairs like we had for decision trees? And do you think we'll get a poor prediction like decision trees, or a much more accurate prediction that would hopefully be close to the 160k salary that this future employee was supposed to have in its previous company? So that's what we are about to find out in this tutorial, and to find out about that, let's build random forest regression. So let's go to our file explorer to set the right folder as working directory. So we go to machine learning AZ, part 2 regression, and here as you can see this is the final round. Well, this is actually the last regression model we were making, which is the random forest regression. So let's open this folder, and that's the right folder we want to set as working directory. Make sure that you have the position salary CSV file, and if that's the case, click on this little button here to set this folder as working directory. Alright, and now let's build the model. So we'll go to our regression template, and this time we will not take everything up to here with the standard visualization of the regression results, but we'll take that instead, because I'm actually giving you a hint. Random forest might be a non-continuous regression model because simply it's a combination of some non-continuous regression models that are the decision trees themselves. So we don't want to take that, we will get the same problem as what we got in decision trees, so we will take this code section here to visualize the regression results. Okay, so I'm going to copy everything, copy, paste it here, and then I'm just going to remove this section because it is not appropriate for our model. So you already have a hint, and you might guess what we will obtain in terms of fitting curve and prediction. Okay, so now let's change the basics. Let's replace regression model here by random forest regression. And here as well. Right. And now let's do the important thing, the creation of our regressor. So, as usual, we are going to do it in 3 steps. First step is to import the right class for the job. Second step is to create an object of this class, which will be our random forest regressor itself. And then third step is to fit our random forest regressor to our dataset using the fit method. So let's do it. The class that we're going to import is the random forest regressor class, another very intuitive name, and we are going to import it from the sklearn.ensemble, here it is, library. So from sklearn.ensemble library, we import the random forest regressor class. So that's the class with capital R, capital F, and capital R again. And now, second step, we create an object of this class, which is the random forest regressor itself. So we're going to call it regressor as usual. Here it is. Now we call the class random forest regressor, so I'm going to copy this. Alright, copy, paste it here, and then now we input the arguments. Great. So let's inspect this class to see what arguments we need to input. So Command I, and here we go. These are the parameters. So the first parameter is an estimators. Can you guess what it is? Well, it's actually written here. It's the number of trees you want to have in your forest. So that's a very important parameter. The default value for this parameter is 10 trees, like we're building a random forest of 10 trees, but don't worry, we will try with a lot more than 10 trees. We will try with 100 trees, and let's go up to 300 trees. So let's input this argument, and estimators equals, and let's start with 10. Okay, so we'll start with 10 and then we'll try 300. Okay, so that's the first parameter, 10 trees in the forest. Great. Then the second parameter is criterion, and remember this is a parameter that we had in the decision tree class that we used to build our decision tree regression model. So it's the mean squared error that's taking the sum of the squared differences between the prediction and the real result. So that's the default criterion, and we're not going to input it because that's the most common criterion, and this will work perfectly with our model and problem here. It's great. Then as for decision trees, you have some optional parameters like max features. The default value for that is auto, so that's fine, because then you see a lot of maximum parameters and minimum parameters. So that's some parameters you can use to improve your model. But let's focus on the essence of the random forest regression model. And so we'll just add this parameter random state as we did for decision tree regression. So we will just input here random state equals 0. Right. So basically what we are only interested in is the number of estimators, that is the number of trees in our forest. So we'll start with 10 and we'll try other values. Okay, so that's the second step, and now the last step of course is to fit our regressor to our dataset. And to do this we're using the fit method that we have to separate from our regressor object by a dot. And here we use the fit method as usual to fit our regressor object to our dataset that is composed of x, the matrix of features, and y, the dependent variable vector. And now we're ready. The random forest regression model is ready to be built. So let's do this without waiting. And what does that mean for the whole code? That means it's ready to be executed. So right now we don't have anything to do. The only thing that we can do as an option is to play around with the number of trees and, choose the best team of trees to build a random forest regression model. So we'll just play around with this parameter and add some more trees and visualize the results and getting the prediction until we get something coherent. So let's do this. Let's execute the sections one by one. So first, let's import the libraries. Here we go, libraries imported. And now let's import the dataset. Here we go, dataset imported. And now let's build the random forest regression model. So as you can see, we shouldn't have any problems. So first, we're building a random forest of 10 trees. Here we go. The random forest is created. So as you can see, all the default parameters were selected automatically. And so now it's time to have fun. Would you like to start by predicting the result or visualizing the regression results? So let's perhaps do this step first, to try some different approaches of our model and then testing the different predictions. But first, before I execute this section, can you guess what is going to happen? With one tree we obtained the shape of some stairs, and it was a non-continuous model, and our previous decision tree algorithm was splitting the whole range of levels into separate intervals, and on each interval it considered the average value of the dependent variable salary. And actually, since we had only one value in the intervals, because we only had 10 levels, this average was only the salary of the level contained in the interval. So that was not interesting at all, and that's why we got a poor prediction. But here we have several trees, so we'll have several stairs. And therefore, how would you imagine a combination of stairs in one dimension? So try to pause on this video and try to predict what's going to happen. And now I'm going to select this section to see what we'll get. So what we'll get is the visualization of some random forest regression composed of 10 trees. And this is what we obtain. So we have the confirmation it's a non-continuous model, as expected, and therefore let's increase the resolution by reducing the step down to 0.01 to, get some more vertical lines that would represent better the non-continuity. So here we go again, let's take this and execute. Alright, that's better now. We visually see some vertical straight lines here that highlights better the non-continuity. So now let's enlarge this and let's interpret. Okay, so the answer to the enigma that I asked you in the previous section and that I was asking you again in this tutorial is that we simply get more steps in the stairs. By having several decision trees instead of one decision tree, we have a lot more steps in the stairs than what we had with one decision tree. And therefore we have a lot more splits of the whole range of levels, and therefore a lot more intervals of the different levels. So each straight horizontal line here, separated by these vertical lines, are one interval that is one split. And the fact that we get more steps in the stairs is actually quite intuitive, because, if we get, for example, this prediction here for the 6.5 level, well, what happened for this prediction is that we had 10 trees voting on which step the salary of the 6.5 level position would be, and then the random forest took the average of all the different predictions of the salary of the 6.5 level made by all the different trees in the forest. And for example, if we take the 4th position level, 10 votes were made each of these 10 votes correspond to one prediction of the level 4 salary made by each one of those 10 trees. And then the random forest took the average of these 10 predictions, and this average is nothing else than the prediction of the level 4 salary made by the random forest itself. And so we get more steps because simply the whole range of levels is split into more intervals. And that is because the random forest is calculating many different averages of its decision trees predictions in each of these intervals. So that's what happened. It's quite intuitive. However, there is something important to point out here, is that if we add a lot more trees in our random forest, well, it doesn't mean we'll get a lot more steps in the stairs. Because the more you add some trees, the more the average of the different predictions made by the trees is converging to the same average. You know, this is based on the same technique, entropy and information gain. So the more you add trees, the more the average of these votes will converge to the same ultimate average. And therefore it will converge to some certain shape of stairs here. So that's important to visualize this as well. And now, since we have our intuition of the visualization of the random forest regression in 1D, let's see what happens with the prediction. So let's execute this, and can you predict what's going to happen? Remember, with our decision tree we got prediction of $150,000, but that was just the salary of level 6, so that was actually not very interesting. But here, as we just saw on the graph, there are a lot more steps in the stairs, so maybe we'll get a much more accurate prediction. Let's find out about that. Let's execute this, and here we go. We get a prediction of $167,000. So a little bit better than with one tree, but wait, we only have 10 trees in our random forest regression. We can build a lot more trees than 10 trees. We can build a random forest with 100 trees, and that's exactly what we're going to do right now to see if our prediction is getting better. So let's try with 100 trees. Here we go, 100 trees now, so let's rebuild the model, execute. Now the model is rebuilt. Let's have a look at it to see if we get more steps in the stairs. And that's what I was telling you. We multiplied the number of trees by 10, but the number of steps in the stairs doesn't seem to have been multiplied by 10. And that's for the same reason an explanation of convergence that I was talking to you about. So actually this is the same idea, this is kind of the same stairs, but maybe that the steps were better chosen to make the ultimate prediction. So let's check that out. We're going to close this and see what happens in terms of prediction. So remember, with one tree we had a prediction of 150k. With 10 trees we had a prediction of 167k. And now let's see the prediction we get with 100 trees. So let's check it out. I'm going to execute this, the model is built. So here we go. And we get, wow, okay, really good. Now we get a prediction of 158k. So it's converging to the supposed previous salary of the employee. And you know, when we applied polynomial regression, the verdict was truth. This employee is not bluffing, and it's an employee that we're happy to hire because not only he's a good fit for the job, but also he's honest. And now it seems that with a random forest of 100 trees, the model is confirming that, because now we get a prediction of $158,000. But let's try if we can get closer to the supposed previous salary of 160k by, for example, increasing the number of trees to 300. Maybe we'll get an even closer prediction, because now the polynomial regression I think is still beating the random forest regression. I don't remember exactly the polynomial regression prediction, but I think it was actually even closer to 160k, or maybe nearly even. Well, let's see anyway if we can get a 160k prediction for our employee's previous salary. So let's check it out. We're gonna try with 300 trees, and let's build this model. Here we go, new model created, new forest created with 300 trees. And now let's visualize these results, but we'll get the same things. We'll not get a number of steps multiplied by 30. We'll get the same shape as before. Here it is, as you can see, it's nearly the same. We get the same number of steps, it's just that the steps are actually better placed with respect to the salary axis for our specific problem. So now let's find out about the ultimate prediction, and I think we'll be able to conclude whether it's truth or bluff. So let's execute this line, and are you ready? Here we go, and we get, oh wow, we get now a predicted salary of 160k right in the spot. We hit the bullseye to predict our future employees' previous salary. And now the random forest regression is beating the polynomial regression model because now we get a prediction that is almost the same as the real value. So right in the spot, congratulations, we actually made our final model. And now I just want to conclude this tutorial by making this transition to one of our future parts, which is actually part 10. In part 10 we will build some ensemble machine learning models. That is, some models that are a combination of several machine learning models. And you know, in machine learning, these are actually the best models. You know, when you have a team of several machine learning models, they can actually make an awesome prediction, because unless we have an Einstein machine learning model in our combination of machine learning models that is the only model to be right, well, you're more likely to get the correct prediction with 10 machine learning models predicting the same thing than with just one model. So that's actually what we did here. Well, we had a team of same machine learning models, which were decision tree regression models, but in the future we'll make a team of different machine learning models. So that's going to be very fun, that's going to be very powerful as well, and I look forward to getting there with you. So now I'm telling you congratulations for two things. First, for building this very powerful regression model, the random forest regression model, and second, for having built all our regression models. We built some linear regression models, some nonlinear regression models, some nonlinear non-continuous regression models, and some nonlinear non-continuous ensemble regression model. So congratulations, you're definitely on your way to becoming some experts in machine learning, but wait for what's coming next. So speaking of what's coming next, I look forward to seeing you in the next sections or next parts, and until then, enjoy machine learning! Hello and welcome to this R tutorial. Here we are at the final round of regression with our final regression model, random forest regression. In the previous section we saw the decision tree regression model, so if now the decision tree regression doesn't have any secret for you, then you will perfectly understand random forest regression. Because a random forest is just a team of decision trees, each one making some prediction of your dependent variable, and the ultimate prediction of the random forest itself is simply the average of the different predictions of all the different trees in the forest. And actually at the end of the previous section about decision trees, I asked you an enigma. The enigma was, knowing the result we got with one tree, what would be the result with 10 trees or 100 trees or 500 trees in terms of visualization and in terms of prediction. So I hope that after watching the intuition tutorial made by Kirill, you actually asked yourself this question and try to predict what's going to happen here with random forest regression. So let's find out about that. We're gonna build our random forest regression model and see what happens. So let's do it. We're gonna start by selecting the right folder as working directory. So it's in part 2 regression, and here is the final regression model we were building, random forest regression. So let's go inside, and that's the right folder we want to set as working directory with the position salary CSV file. So let's click on this more button and set as working directory. All good. And now let's take our regression template to build this model efficiently. So we're actually going to take everything from here to the bottom, but we will only include this code section to visualize the regression model results, because you understood that the decision tree regression model is a non-continuous regression model, and since random forest is a combination of decision trees, then it's a combination of non-continuous regression model, and intuitively we understand, we can guess that the random forest regression model is not going to be continuous either. So since this code doesn't work for non-continuous regression model, we will actually use this one that works perfectly for it. So I'm going to copy this, paste that here, and remove this section that is non-appropriate for non-continuous regression models. Here we go, and now the template is ready. Let's change the basics. Let's replace here regression model by random forest regression, visualizing the random forest regression results, and fitting random forest regression to our dataset. Okay, great. So now let's build a model, which is in this section here. So let's remove this, and as usual we're going to import the right library for the job and then use a function to build our random forest regressor. So the package we're going to import is called random forest. So for those of you who don't have the package installed in your packages here, well, you can check it out. Mine is already installed because I used it before, but I'm going to write this line here for those of you who need to install it. So install dot packages parenthesis and in quotes random. So no capital R, but then capital F-O-R-S-T. Alright, random forest. And so I'm not going to install it because mine is already installed, so I'm going to put that in comment. But if you want to install it, you just need to select this line as I just did and press Command and Control plus Enter to execute it, and this will install the package properly. But here I'm going to put it in comment by pressing Command plus Shift plus C. Here we go. And now what we have to do is to add this, library random forest to actually automatically select the box here to import automatically the random forest package when we execute the whole code or the section. So that's important. And now time to build the regressor. So let's do it. We're going to call regressor as usual to keep things simple, then equals, and now the function that we're going to use is also random forest, written the same. And so now let's add some parentheses, and now let's press F1 to have a look at the arguments. Okay, so the arguments are here, and the first argument is data. But as you can see, it specifies that it's an optional data frame, and we could use this argument to build our regressor, but we're going to use the main arguments to specify, the independent variables on one side and the dependent variable on another side. And to do this, we're going to use these two arguments, x and y. So x will contain the matrix of features, that is the independent variables, and y will contain the dependent variable vector, that is the salary column. So let's first input these two arguments. So the first argument is x equals, and so we have several ways to take our independent variables. So one of the ways is to take our data set here and then choose the right columns of the independent variables. And our data set is composed of two columns. The first column indexed by 1, which is the independent variable column, and the second column indexed by 2, which is our dependent variable column. So here we need index 1 because we want to take the independent variable. Alright, now next argument. The next argument is y, the dependent variable vector. And now, as you can see, y is expected to be a response vector. It's actually a vector. And here it's expected to have a data frame. So by using this one index into brackets here, I actually import a data frame. But here, to get a vector, I actually need to use another trick, another technique, which is to use the $sign and then the name of the column, which is, of course, salary. And that will give me a vector. So just to recap, this syntax here will give me a data frame because we're taking some sub data frame of our original data frame data set. And here, by using this $sign syntax here, taking dataset $sign salary, I'm actually taking the salary column of our dataset, but that will make it a vector. And that's exactly what we want because the y argument here is expecting a vector. So we're all good. And now we actually need to input a third argument. Can you guess what that is? For those of you who followed the Python tutorial, well, you will guess what it's going to be. It's actually going to be n-tree, the number of trees in the forest. Well, of course, we're building a random forest, so it's actually a lot better if we can choose the number of trees that we build in our forest. And it's even better considering the fact that we're going to play around with different number of trees. That is, we're going to start with 10 trees, with a forest of 10 trees, and then, we'll try with a lot more than 10 trees, like 100 trees or 300 trees or 500 trees. So that's why we're going to input the third argument n-tree, and we're going to start with 10 trees. Alright, so let's start with this, and that's all the arguments we need to build our random forest. We only need the independent variables, the dependent variable, and the number of trees. And that will already make a robust random forest regression model. And then we will make it even more robust by adding more trees in the forest. But before we continue, let's set the random factors to something fixed so that we all get the same results. So in Python we use the random state parameter equal to 0. Here we can do the same on R by using the set.seed function. And then in this function we actually input a seed, and we can use whatever seed we want. In Python we usually take 0 or 42, and in R what we like to do is to take either 1, 2, 3 or 1, 2, 3, 4. So let's use this seed to all get the same result, and that will make this tutorial easier to follow if you're coding at the same time. So now we're all good. We're actually all good with the whole code. We don't have anything to replace. The only thing that we'll do now is to, try several random forests with several number of trees and look at the visualization results and look at the prediction to see if we're getting close to the supposed 160K previous salary of our new employee that is about to be hired. So let's do it. Let's execute the sections one by one. So let's import the dataset first. Here we go, dataset well imported. We make sure we have our two columns, the independent variable level and the dependent variable salary. Perfect. Now, no need to split the dataset into the training set and the test set. No need to apply feature scaling. And now time to create our first random forest. So let's do this. Let's execute this code section here. And here it is, random forest well created. Perfect. So now it's time to have fun. Would you like to visualize the result first or getting the prediction? Well, first, let's maybe visualize the results because we want to make sure we have the right model and we want to validate it. Because we will try several number of trees. Here we are starting with 10 trees, so we want to see if it looks like a correct model. So I'm going to execute this section. Here we go, and let's see what we'll get. Okay, so first of all, this looks fine. We don't seem to have any problem here. The only thing that we can improve very quickly is actually, those straight lines here that are supposed to be vertical. And to get a better representation of this, we just need to increase the resolution as we did for decision tree regression. So let's add 0.01, that will be sufficient. And let's re-execute this. And now much better. It almost looks like it's some vertical straight lines representing better the non-continuity. And so now what can we say? Let's zoom on this plot to have a better look. And now let's integrate. Okay, so the answer to the enigma that I asked you in the previous section and that I was asking you again in this tutorial is that we simply get more steps in the stairs. By having several decision trees instead of one decision tree, we have a lot more steps in the stairs than what we had with one decision tree. And therefore we have a lot more splits of the whole range of levels and therefore a lot more intervals of the different levels. So each straight horizontal line here, separated by these vertical lines, are one interval that is one split. And the fact that we get more steps in the stairs is actually quite intuitive because, if we get, for example, this prediction here for the 6.5 level, well, what happened for this prediction is that we had 10 trees voting on which step the salary of the 6.5 level position would be. And then the random forest took the average of all the different predictions of the salary of the 6.5 level made by all the different trees in the forest. And for example, if we take the 4th position level, 10 votes were made. Each of these 10 votes correspond to one prediction of the level 4 salary made by each one of those 10 trees. And then the random forest took the average of these 10 predictions, and this average is nothing else than the prediction of the level 4 salary made by the random forest itself. And so we get more steps because simply the whole range of levels is split into more intervals. And that is because the random forest is calculating many different averages of its decision trees predictions in each of these intervals. So that's what happened. It's quite intuitive. However, there is something important to point out here is that if we add a lot more trees in our random forest, well, it doesn't mean we'll get a lot more steps in the stairs. Because the more you add some trees, the more the average of the different predictions made by the trees is converging to the same average. This is based on the same technique, entropy and information gain. So the more you add trees, the more the average of these votes will converge to the same ultimate average. And therefore it will converge to some certain shape of stairs here. So that's important to visualize this as well. And now, since we have our intuition of the visualization of the random forest regression in 1D, let's see what happens with the prediction. So let's see what prediction we get. Remember that this employee said that its previous salary was 160K. And now let's see what says our random forest composed of 10 trees. So let's execute that. And it says that the previous salary was $141,000. But that's actually a very dangerous prediction because we are way below the 160K salary that this new employee said to have in its previous company. So if we trust this prediction, we would actually think this employee is bluffing. But no worries, we will not stop here. Right now we're going to try a random forest with a lot more than 10 trees. So let's pick, for example, 100 trees and let's see what we'll get. So I'm going to rebuild the model. Here we go. And now let's look at the graphic results. And as I was telling you, we don't get much more steps in this plot of our new random forest regression. You know, we multiplied our number of trees by 10, but the number of steps was definitely not multiplied by 10. If we compare, we can compare that very quickly. This is the previous plot, and this is the new one. 10 trees, 100 trees. We can see that we have maybe a little more steps, but definitely not 10 times the previous steps. So the reason for this, the explanation, is related to this convergence idea that I talked to you about. And so what changes here with 100 trees in terms of the plot is not the number of steps that was increased, but a better choice, a better location of the steps in the stairs with respect to our salary axis. That means that maybe the steps are better located to make our ultimate predictions of the salaries of each of our level from 1 to 10 incremented by 0.1. So to check that out, we simply need to make our final prediction to predict the salary of the 6.5 level. So let's recap. The employee is saying 160k. Our random forest with 10 trees said 141k. And now let's see what say our random forest with 100 trees. Execute. And now it says 166k, so much better. We're getting close to the supposed real salary of 160k, and besides, we're now actually on the good side of the negotiation because we would no longer think that this employee is bluffing. So, since the prediction seems to be improving as we increase the number of trees, let's actually try with 500 trees. So that's a huge forest we have now, so let's execute this to build our new huge forest of 500 trees. Here we go, new forest created. Let's have a quick look at the visualization plot results, but it's going to be the same thing. We will not get a lot of more stairs, maybe a little more. Well, actually, let's check it out. Well, definitely not. We seem to have the same number of steps in the stairs, but as I was telling you, each of the steps in the stairs might actually be better located to make each ultimate prediction of the salaries for each of the 10 levels here. So, the best way to check that out is actually to get our ultimate prediction of the salary of the 6.5 level, and let's check it out. Let's see if we get a better prediction than 166k. Executing, and right in the spot. We hit the bullseye with 160,458 predicted salary. So awesome job that this random forest with 500 trees just did here, because it predicted almost the same salary as the supposed 160k salary that this future employee said to have in its previous company. And actually so far, before we made this random forest with 500 trees, the best model that made the closest prediction to this 160k salary was the polynomial regression model, and now the random forest regression is beating the polynomial regression model, because now we get a prediction that is almost the same as the real value. So right in the spot, congratulations! We actually made our final model. And now I just want to conclude this tutorial by making this transition to one of our future parts, which is actually part 10. In part 10 we will build some ensemble machine learning models. That is, some models that are a combination of several machine learning models. And you know, in machine learning, these are actually the best models. You know, when you have a team of several machine learning models, they can actually make an awesome prediction, because unless we have an Einstein machine learning model in our combination of machine learning models that is the only model to be right, well, you're more likely to get the correct prediction with 10 machine learning models predicting the same thing than with just one model. So that's actually what we did here. Well, we had a team of same machine learning models, which were decision tree regression models, but in the future we'll make a team of different machine learning models. So that's going to be very fun, that's going to be very powerful as well, and I look forward to getting there with you. So now I'm telling you congratulations for two things. First, for building this very powerful regression model, the random forest regression model, and second, for having built all our regression models. We built some linear regression models, some nonlinear regression models, some nonlinear non-continuous regression models, and some nonlinear non-continuous ensemble regression model. So congratulations, you're definitely on your way to becoming some experts in machine learning, but wait for what's coming next. So speaking of what's coming next, I look forward to seeing you in the next sections or next parts, and until then, enjoy machine learning!
Last, we will discuss about the evaluating regression model's performance, and how to do it in practical way.
R squared. This is a very interesting parameter. A lot of people use it, and sometimes they use it without knowing the underlying principles of R squared. So let's quickly quickly get a understanding of what R squared is, because we will be using it too. So last time we stopped over here, we talked about the simple linear regression being constructed through the ordinary least squares method, where we are minimizing the sum of squares of those differences yi minus yi hat. And basically we are looking at what the model is predicting and what is actually happening at a certain level of experience, or at a certain level for the independent variable, and we're looking at that difference, we're squaring it, we're summing it for all of the observations we have, we're counting that sum, and then the line that has the smallest sum will be the best fitting line, or will be the simple linear regression model. So let's get rid of that call out for a second, and let's remember this value. So we'll need it just now, and in fact this value has a name. It's called the sum of squares of residuals. So we'll just label it SS res. And now let's do something else with our chart. We'll get rid of those lines. So this is our raw chart with the observations, and instead of drawing the regression line, let's draw the average line. So this is your average salary across all of your observations. Now let's do the same exercise and project our observations onto this line. And now if we calculate the distances, the red distances, and we square them, then it'll look like this. It'll be yi minus y average squared, and then we'll take the sum of all of these distances. Now this value also has a name, and it's called the total sum of squares. And what R squared is, R squared equals to 1 minus sum of squares of residuals divided by total sum of squares. And so what this is saying is that there will always be a sum of, or total sum of squares, right? So the average, not all, your records are not always going to be all equal to the average, otherwise it's a very boring data set. So sum of the total sum of squares will always be some sort of value. And what you're trying to do with your regression is you're trying to fit a line to minimize, as we discussed previously, to minimize the sum of squares of residuals, to make it as small as possible, right? So in a way, the way to think of it intuitively is the average line, which we have on the chart right now, is also a type of a trend line. It's just horizontal, right? It's not sloped, it's just a horizontal trend line, but it kind of also is. So you can think of it as a model that is fit to a dot. It's not the best model, but it's just y average. So what you're trying to do by fitting a sloped line and minimizing the sum of squares of residuals is you're trying to fit the best line. And what R squared is telling us is, it's telling us how good is your line compared to the average line, which anybody can think of, right? So it's not hard to take the average. You take a calculator, you get the average. But in order to fit the best fitting line, you have to actually run a linear regression. And if you look at the formula, so you're trying to minimize SS residual, right? So sum of squares of residual. So on the right over there, that part of the formula, as you minimize SS residual, it goes smaller. It always becomes smaller. And that way, SS residual divided by SS total becomes smaller, and 1 minus SS residual divided by SS total becomes greater. So ideally, if your SS residual is 0, so basically your trend line that you're modeling goes through all your records, then in that case R squared is equal to 1, and that's the ideal scenario. But that normally never happens, so the closer R squared is to 1, the better. The further away it is from 1, so the lower it is, the worse. A good question is, can R squared ever be negative? The answer is yes, of course R squared can be negative, and that is if your, for instance, SS residual actually fits your data worse than your average line. It's hard to do, but you gotta try, because if you just draw a random line, I guess, then facing the wrong way, so here would be going downwards, then probably yes, you would get a negative R squared. So that means that the model is completely broken. It's better to use the average and even to use the model. But normally, so R squared is normally between 0 and 1, never gets greater than 1, and the closer it is to 1, the better. All right, so this is the fun part, adjusted R squared. So here we've got a simple linear regression. We've talked about how the R squared is derived. So what the formula for R squared is, it's equals to 1 minus sum of squares of residuals divided by total sum of squares, where sum of squares of residuals is the sum of squares of the distances from the observations to your fitted line. So we don't see it here. That's your simple linear regression line that we fit onto our data, and the total sum of squares, we can see it here. So that's the total, the sum of the squares of those red lines we can see here. So the difference between your observations and the average. So basically R squared is telling us how well is your model fitted to the data, and in fact how much better is it fitted than the average line that you can just draw through your data very easily. So let's get rid of all of that and put our R squared formula on the left for a second. Now, we talked about R squared for a simple linear regression. Well, the same concepts apply for a multiple linear regression. So for instance, with two variables, R squared would be calculated in the same way. We're just not going to go through all these derivations right now because it's just easier to visualize the way we've done it, and exactly the same concepts apply to a multiple linear regression. And still, so what that means is that the ordinary least squares method is used, and the best fitting multiple linear regression is the one that has the least sum of squares of residual. So you're trying to minimize the sum of squares of residual. And why am I bringing that up? Well, we'll need that in a second. So we want to use R squared, as we discussed, as a goodness of a fit parameter. So the bigger it is, the better. The closer it is to 1, the better your model. And that's awesome. We can totally try doing that, but there is one problem. And the problem is, or starts to occur, when you add more variables to your model. So here you can see we've got two variables in our multiple linear regression. What will happen if we add a third variable to our model? Think of it as an example. Let's look at that example with salary. So your salary equals to a constant 30,000 plus 10,000 times the years of experience, plus, for instance, B2 could be a constant coefficient times the number of qualifications you have, and I don't know, B3 could be how much money you brought the company in the previous year. So if you're a salesman, for instance, so a coefficient times the amount of dollars that you brought the company in the previous year, something like that. So you can keep adding on variables that you think are actually impacting the outcome, so are impacting the dependent variable, and you want to fit a model and see, you know, if it's better or not. So in this case, we're adding a third variable. We already have a model with two variables and it works okay. And now we want to add a third variable and see if maybe using the third variable we can fit our model even better. So we can create an even better model with three variables. So how can we judge that? After we've added our variable and we've run the model, we can look at the R squared. Did the R squared get better or worse? So in fact, did the R squared increase, or did it decrease or stay the same? So the problem here is that R squared, because of these two things, R squared will never decrease. And let's go through that in a bit more detail. I'm going to use my mouse here because this is quite an important part. So R squared over here is equal to 1 minus sum of squared of residual divided by sum of squared of total. So once you add a new variable to your model, right, is going to somehow affect what the model looks like. And the fact that we're trying to minimize the sum of squares of residual, what that means is that either this new variable will help minimize the sum of square of residual, somehow the regression process will find a way to give it a coefficient that will help minimize the sum of square of residuals, and then and in that case R squared will happen to R squared. It'll be 1 minus something that is less than it used to be, right, divided by the same value, because by adding a new variable, we're not affecting the observations, we're not affecting the averages of the observations, right? This does not change. So by adding a new variable, the regression process through this condition will definitely try to minimize this value, make it even smaller than it is currently. And that way, this whole part will decrease and this whole part will increase. So your R squared will increase. If it so happens that the new variable that's added, whatever coefficient you give it, a new coefficient you give it, if you cannot decrease SS residual, right, what will happen? Well, this coefficient will just become 0. It rarely happens. I don't think I've ever seen a coefficient like be exactly 0, and I'll tell you just now why. But in the worst case scenario, the regression process will say, nah, this variable is, you know, completely just making the model definitely worse, so I'll just put a 0 instead of this coefficient and forget about it. And that way SS residual won't change and R squared won't change. So you only have two options. Either R squared will increase or it won't change at all. So R squared will never decrease if you add variables. And why I say that B3 is never equal to exactly 0, because there can always be, or there will always be, at least a slight random correlation between the independent variable and the dependent variable. It doesn't matter what you put in here. So even in the example when we're looking at salary, so salary equals years of experience plus how many qualifications the person has, and then we can add in what is the last digit of the person's mobile number, right? Of course, that is not going to, it doesn't have any correlation with the independent variable whatsoever. Well, there's no causative factor, there's no association between the two. The last digit of your mobile number has no effect on your salary. But if we add it in, and there will randomly be a slight correlation, you know, it'll just be a random correlation, and the regression process will pick it up and will give it a coefficient, and R squared will probably decrease by that tiny little, or increase by that tiny little bit. And so that is why there's a problem with R squared. You can add variables and you will not know if those variables are helping your model or if they're not helping, because your R squared is biased. It's basically always increasing regardless of the actual improvement or non-improvement in fit. So we got to come up with a different parameter to measure goodness of fit, and that is where adjusted R squared comes in. This is the formula for our adjusted R squared. Here P is the number of regressors, so the number of independent variables, N is the sample size, so it's over here. Now they say that adjusted R squared has a penalization factor. It penalizes you for adding independent variables that don't help your model. And let's talk about that. That's the important bit about adjusted R squared. So P is the number of independent variables. Let's look at P. P here is in the bottom, in the denominator. That means that when P increases, when you increase the number of independent variables, this whole part decreases. And when this whole part decreases, the denominator decreases, the ratio increases. And as the ratio increases, this whole bit increases as well. And as this whole bit increases, 1 minus this whole bit decreases. So as you can see, as you're adding more regressors, the adjusted R squared is decreasing. It's going further away from 1. And that is the important part. Also, you can see here what happens when R squared increases. When just normal R squared increases, so this part decreases, right? 1 minus R squared decreases. And that means that this whole part increases. So you've got a battle here. On one hand, R squared, by adding a new variable, you're increasing R squared, so you're increasing adjusted R squared. But on the other hand, by adding a new variable, you're increasing P. So you're decreasing adjusted R squared. And in that sense, it's a fair battle here. If your variable is not good, is not helping the model, then adjusted R squared, this will be an insignificant increase, and this penalization factor will actually drive R squared down, adjusted R squared down. If on the other hand, your new variable that you added is helping the model a lot, then the increase in R squared will be substantial, and it will overwhelm this penalization factor. So even though you'll still get penalized for adding a variable, the increase, the benefit to the model will be so great that even the adjusted R squared will go up. And so that's how the adjusted R squared basically works. It's a very good metric. It helps you understand whether you're adding good variables to your model or not. And we'll be using adjusted R squared throughout this course to make sure our models are robust when we're building them. Great to see you back here, and today we're going to look at the handy trick that will help your models become more robust. Before we continue though, I wanted to quickly recap on what we did last time. And what we did is we used the backward elimination method to construct a multiple linear regression using our data, and through that method we constructed 4 separate models. You can see them on the in the background here. So model 1, 2, 3, and then 4. And when we got to model 4, we were only left with 1 independent variable spent on research and development, because all of the other ones were eliminated. And basically we completed the backward elimination process. However, we were left with kind of a feeling that maybe we shouldn't have excluded the last variable. And why is that? Well, first of all, we saw that this p-value is not that much bigger than the significance level that we selected. We selected a significance level of 0.05. The p-value here is 0.06, so just a bit greater than the threshold. So that kind of leaves us with a feeling maybe we shouldn't have excluded that variable. The problem here is that these methods, these stepwise regression methods, they are very arbitrary. So once you select your significance level threshold, you gotta stick to it, right? We selected 0.05, this one's 0.06, so that's greater, and we just gotta cut it off and not look back anymore and just proceed with the method. So how can we improve our method of building models to assess situations like that and give, like an extra opinion, or have another criteria to tell us whether or not we should have actually kept this variable? And there is a way, and we're going to talk about it right now. So let's look at this top part over here. The top part is responsible for the variable. So you have the coefficients and you've got the p-values and so on. So we've talked about it quite extensively. But now let's look at the bottom part, the second part of our report. And here, as we discussed before, we've got the stats that are for the model as a whole. So how well it's been fitted, how well it's working, and so on. So the stats that we'll be looking at today are R squared and adjusted R squared. And they will help us come up with a cool approach, or great approach, to improve our backward elimination method. So we already talked about both the R squared and adjusted R squared in the section of this course. However, if you chose to skip that section because you're not interested in the formulas and so on, then I'll quickly recap for you now. So R squared over here is basically a characteristic or a parameter of your model which tells you about the goodness of fit, so how well your model has been fitted. And R squared can never be greater than 1, and you want it to be as closest to 1 as possible. The closer to 1 it is, the better your model is deemed to be fitted. However, R squared is biased, and it's biased in a way that the way it's constructed and the way these models are run, so the ordinary least squared method, it doesn't allow R squared to ever decrease. So the more variables you add to your model, the greater R squared will be. So basically what this means is that as long as you keep adding variables, R squared will always grow. And we can observe that here. So if we start from the end where we have only 1 variable, you can see that R squared is 0.94. Then R squared became, well, if we go this way, it's 0.95. Then it's 0.9507. So as you can see, the more variables we have, the greater R squared gets. And that's always going to be the case just because of the way R squared is derived. And moreover, you can even include completely random variables. So if I throw into this model, I throw another variable, which is basically the temperature outside, like air temperature outside right now, then and I throw that in as an independent variable. Of course, it's not a predictor. It can't predict profit of a company that works in New York or California, but R squared is still going to grow and is going to imply that our model is now even better fitted. So that way R squared is biased. And that's where adjusted R squared comes into play. Adjusted R squared is very similar to R squared. It's got a very similar formula, but it actually has a penalization factor. So basically, just like R squared would grow if you add more variables, adjusted R squared would also grow, but there's a penalization factor which makes it smaller, which reduces adjusted R squared as you add more variables. So there's kind of these two effects battling each other. On one hand, it's growing because of the way it's constructed. On the other hand, the penalization factor is penalizing you, or penalizing the adjusted R squared, and reducing it every time you add a variable. So basically, if the variable that you added doesn't make R squared grow that much, like for instance here you can see 0.9505 to 0.9507, so it only grew by a fraction, very, very small amount. Well, if that happens, then the penalization factor is going to overwhelm this growth, and therefore the adjusted R squared is actually going to decrease in that scenario. And that way we can use, and we will use, the adjusted R squared to watch the goodness of fit of our models and how it changes. So let's go ahead and do that. Let's observe the adjusted R squared in our method. What was the adjusted R squared here? It was 0.94. Then once we excluded administration expenses, adjusted R squared went from 0.945 to 0.9475. So as you can see here, adjusted R squared went up. We reduced, basically what that means is that the model is now better. It's fitted better. It works. These variables in this combination fit the profit variable, fit this model to explain the profit variable better than these variables in this combination to explain the profit variable, which is good. It's a good step. Okay, so that means we improved our model. Here adjusted R squared is 0.9475. Let's see what had happened to it when we move to the next step. In the next step, adjusted R squared is 0.9483, so it went up again, meaning that once again we improved our model. So altogether these variables are doing a better job explaining profit than these variables together are doing a job explaining profit. That's great, we improved our model again. And now let's see what happens when we take out the last variable, marketing spend. So we went from adjusted R squared 0.9483 to adjusted R squared 0.9454. And what does that tell us? Adjusted R squared went down. It went down by 0.003 approximately. So that means that this model, this new model, is actually worse than this model. So this model was better fitted to predict or explain the variance in profit than this model is doing so. So there you go. So even though we excluded a variable according to our backward elimination method, this variable shouldn't have been excluded because it was with this variable, this model is actually working better. And that is your takeaway handy trick how to observe your models and how to create them. You don't only just follow the backward elimination or whatever method that you're using and arbitrarily follow the rules. Just instead follow the rules, but also watch the adjusted R squared and see if it's actually improving. So if it's growing, then you're doing the right thing. As soon as you see the adjusted R squared drop, then you have to stop and question, did I just do the right thing or not? And you know, what is the trade-off of excluding a certain variable or the opposite of including the certain variable? So adjusted R squared is kind of your indicator how you're going along the way. But that's it for today. Hope you find this useful and hope you'll find ways to apply this in your actual work. I look forward to seeing you next time, and until then, happy analyzing. And finally, interpreting coefficients. In front of us here, we've got the 4 models that we built in our backward elimination method. And as we agreed, model number 3 is the best one, it's the best fitted model. And if we were to deliver a model on our project, it would be this one. So let's go ahead and start interpreting coefficients by looking at this model. Here we've got 2 variables, R&D spend and marketing spend. So it's basically how much companies are spending on their research and development and on their marketing. And we've also got the constant, and we're predicting profit. So these coefficients here, these are B1 and B2, what they're telling us is that, so how to interpret them. First of all, you look at the sign. If the sign is positive, that means your variable is correlated with your independent variable is correlated with your dependent variable, meaning that if you change the value of your independent variable, then then you can see that the dependent variable will be changing in the same direction. So basically, if you'll be increasing spend on R&D, then your profit will be increasing. If you're increasing spend on marketing, then your profit is also increasing, which makes sense, right? So if you're spending more on research and development, making your product better, then probably your profit should increase eventually as well. Same thing with marketing. The more you spend on marketing, the more you sell, and therefore the profit should also go up. And that's the sign. If the sign is negative, if the sign were negative, then it's the opposite effect. So basically you increase your independent variable and your dependent variable decreases. And now let's look at the magnitude. So here you can see right away that the magnitude is higher for R&D spend and the magnitude is lower for marketing spend. Magnitude is always tricky with regressions. Be careful with magnitude. Sign is kind of, pretty obvious. It's one way or the other. Magnitude can really trip you up. And I can give you an example here. So you might think that, okay, right away, magnitude is greatest. So this coefficient for R&D spend is bigger than the marketing spend coefficient. So definitely R&D spend has a bigger impact. Well, what if I tell you that I could easily, without changing anything in the regression, I could easily make this coefficient bigger by a lot, by 1,000 times bigger than R&D spend? Well, it's easy to do. All I have to do is say marketing spend, instead of looking at it in dollars, how about I look at it in a fraction of a cent? So every marketing spend, or let's look at it in cents. So marketing spend, instead of counting it in dollars, let's count it in cents. Right away, because our variable has gone down 100 times, our coefficient will proportionally increase, so it'll go up 100 times. And if I change my data and replace everywhere marketing spend with cents, and everything else I will leave the same, then I rerun this model, I guarantee you that the coefficient here will actually become 2.99, so it will just increase 100 times. Everything else will stay the same. And that way, right away, you'll see, oh wow, the marketing spend coefficient is greater, so then marketing spend has a bigger impact on your dependent variable profit. And that's a mistake that a lot of beginners make. You should not fall into this trap. Magnitude is a tricky thing, and the way to think about it is always say magnitude in terms of units of the independent variable. So the correct way to analyze this is, even without knowing what they're measured in, maybe this one's measured in thousands of dollars and this one's measured in dollars. I don't know, for instance, although I do know, of course, I've seen the data. But if, say, I don't know, you can still make a conclusion. All you have to say is R&D spend has a greater impact on profit per unit of R&D spend than marketing spend has per unit of marketing spend. And that's all. So basically, even if they're measured in different things, by saying per unit of the underlying variable, you are protecting yourself from that error that they are measured in different things. And moreover, imagine if they're measured, one's measured in dollars, the other one's measured in kilometers or something like that. You can't compare dollars and kilometers, right? But you can always say per unit. And this leads us to the actual interpretation of these variables or these coefficients. What does it mean? So this means 0.79 means that for every unit, if you keep all other variables constant, so you only have one other variable. So if you keep everything else constant, but you are able to adjust R&D spend for in this model, or for a hypothetical company, for every dollar or for every unit of R&D spend that you increase, your profit will increase. According to this model, your profit will increase by 79 cents. That's exactly what this coefficient is saying. And so for every unit that you decrease in your R&D spend, your profit will decrease by 0.79 of a unit of profit. And because R&D spend is measured in dollars and profit is also measured in dollars, that means so for every unit increase in for every dollar increase in R&D spend, your profit will increase by 79 cents. So let me just repeat that again. That you are looking at units increase in R&D spend, they translate through this coefficient into units increase in profit. So if your profit was measured in apples, then a $1 increase a 1 unit increase, this is always going to be true, 1 unit increase in R&D spend will drive a 0.79 unit increase in profit, and of course of the profit units. So let's turn that into dollars and apples. A $1 increase in R&D spend will drive a 0.79 or 80% of an apple increase in profits. So here you're talking about units of R&D spend. In profit, you're talking about units of profit, and this coefficient, it links them together. So as long as you say per unit, you're fine. Once you already know what these variables are measured in, then you can start comparing them if they're on the same scale. And in this case, they are on the same scale because everything's measured in dollars here. And you can say that a $1 increase in R&D spend drives 79 cents increase in profit. A $1 increase in marketing spend drives only 3 cents increase in profit. So basically, if you're the venture capitalist, which companies you're going to invest in? Well, from this model, you're going to decide that you should invest into companies that are spending more on their R&D. There may be lots of reasons behind this, and this is not just a random fact. This could be true in reality because profit is revenue minus expenses. Maybe marketing does drive a lot of revenue to your company, but at the same time, maybe for these specific companies that we're looking at, their expense, the cost of marketing, so the prices that they pay for marketing is so high that the increase in profit, the net increase in profit is actually marginal. So the marketing is eating up a lot of the revenue that it's creating, whereas R&D is is creating a lot of revenue, and a lot of it is actually staying in profit, something like that. But we're not worried about that right now. That's more financials. What we're doing is we're delivering a model. So that's how you interpret coefficients. With a linear regression, it's very simple. Just remember about that per unit trick or tip, I guess, because if you forget about that, you can make the wrong conclusions. Otherwise, it's all pretty simple. The last thing that I wanted to mention here is that you can see that every time we run a model, the coefficients change. So what that is telling us is that coefficients actually only talk about the additional effect of every single variable, given that the other variables are already in place. So for instance, in this example, your coefficient of marketing, which is 0.029, means that given that R&D spend is already in your model and it's fixed, then marketing spend adds additional, contributes this additional effect of 0.0299, meaning that if you were to run a different model and take out R&D spend, then the coefficient would be completely different. And that's what we see here, that when we take out marketing, the coefficient for R&D spend is taken out. So that's another thing you should remember about, that coefficients merely portray the additional effect that every single variable brings into the model. Hope you enjoyed this tutorial, and I look forward to seeing you next time. Until then, happy analyzing.